Once you say, right, so that is very crucial. When you say spare part inventory, it will become very, very crucial. What that mean? The mean is, suppose, let's take another example here. When you say spare part inventory, suppose you are in defense sector, because it's very crucial in defense sector. Suppose you are in the defense sector and you buy a very good part. You have to buy some part from Russia or France. Let's just example, because we are taking the planes from there, right? Now, one particular part, the cost of that part, let's say 100 crore, because that happens. The part of this particular, the cost of this part is 100 crore. So you cannot keep multiple parts as well as you cannot say, I don't want any part. Suppose suddenly you required any part, then the cost of traveling, sending the request, doing all formalities, and getting that parts will cost, let's say, 4 months of the time. So that's why maintaining the inventory is very important. So when it will come into the picture? If you are aware what is the remaining useful life of the particular part, you can easily find out your inventory. You can easily manage your inventory. Because based on the lifespan of the equipment, you can easily manage the inventory. So this is the way how predictive maintenance remaining useful life will help you to plan many things. So few examples. If you say this is like a motor, big motor here, right? There are lots of chamber. So you can say here we have the fan, we have the LPT, we have the chamber and all those things. And consistently we are monitoring the data to find out the remaining useful life. What kind of health data can be? It can be the temperature, it can be the pressure, it can be the RPM, and many such data we are consistently monitoring, right? Because these sensors are deployed in the system to monitor those all things, right? So once you say I deployed those things, we have sensors which is consistently monitoring. Why not we will just utilize those things to use, or you can say to find out the remaining useful life. And you find out like the top deep learning models help us to reduce or to find out the remaining useful life 35 to 49% better than the traditional method that we was using previously. So we'll see today how we can do that. Similarly, if you say in the oil field, this is another example here, right? And that is these are the proved example. Proved means it's already happened. So in the traditional methods, we are getting, so you can say every failure, the cost of, as I told you, every cost of the failure is $150K, right? Per day per well. And how many wells we have? Around 60K wells. So you can say if a particular well motor is not operating, right, then it is giving you the cost of $150K. So there are multiple methods using the ML techniques, right? And then they are able to find out only around 50% of the things. And the detecting of the failure is also late. They are not very advanced in nature, right? And producing lots of false alarm. What false alarm indicate? False alarm means even there is no failure, there is no failure going to happen, but your system is saying there is a failure. So what is the impact of that? The person will stop the plant for some time to check where is the problem. That is also not a good idea. 50% means it's a very big number. 50% false alarm. Whenever you use the deep learning methods, 93% we are able to detect correctly. And that's why we are doing this workshop. right? To understand. As I said, these are just examples. You can apply these methods in different places, various organizations, right? Similarly, you can say 10% of false positive. False positive means there is no, there is no, yes, there is no fault, but still we are saying there is a fault. That is the false positive, right? So previously it was 50% of the false positive alarms. Now with the help of machine deep learning methods, we have only 10% of the false positive, reduced by 40% around, right? And that will, like, along with that, if you say the anomaly detection, with this deep learning based method able to detect the anomaly and yield is like this anomaly, if we are not able to detect, this much cost we have to pay, around $300K, right? So that we are able to reduce. One side we are detecting the failure earlier, another side we are trying to give the intuition there is something wrong happen, some anomaly is going to happen. It's not the behavior is changed, or you can say the behavior is changed from normal behavior, so please check the things. That is the anomaly. When anomaly comes into the picture, whenever you do not have any bad data available, your failure doesn't happen, then you of course looking forward for the anomaly when your system behavior is changed, right? So what this entire workshop will do, we'll talk about the data collection, augmentation, defining different performance metrics, right? We'll talk about several deep learning models such as autoencoder, LSTM based model. We'll also talk about pandas data frame and other data frame. We'll also talk about imbalanced data. So these all will be the part of the workshop that we will do today, right? Then we will see how we'll find out the categorize the data, what different kind of classification we'll do, and how to use the CUDF. What this CUDF? It is, so CUDF is the GPU based library similar as the pandas. So what you are doing in the pandas, this is CPU library, CPU based library, which is running on the CPU. And if you want to make it faster, you want to utilize your GPU, then CUDF comes into the picture, right? So CUDF is part of the rapids that we will utilize to make our system faster, to make the training faster. So this is broad overview of the workshop. In the lab 1, we'll talk about the XGBoost method. In the lab 2, we'll talk about the LSTM based model. And in lab 3, we'll talk about the autoencoders, right, to solve the problem, right? Now let's talk about what is XGBoost. So many of you may be already aware about some machine learning methods. So there are some methods which are tree based method. So one of the very popular tree based method is the decision tree, right? Similarly, so decision tree is something where we are making only one single tree to solve our problem, one tree to solve the entire problem. That is known as the strong classifier, or you can say strong model, one single model which is strong in nature, right? That is the decision tree you are making, one single decision tree for the particular task. Then there is a concept of ensemble method. So here we have the concept of ensembling. What ensemble is saying? Ensemble is saying if you have multiple models which have the local information available, and if you combine the results of all of those models, then they will be much better than the single bigger model. That is the ensemble, right? And that is inspired from Concord's theorem. Concord's theorem is very old theorem. What Concord's theorem is saying, if you are doing just better than random guess, and if you have such multiple models available, then if you combine their results together, they will definitely give the correct answer. That is the Concord theorem, right? So what ensemble is saying, if you have multiple such models, we will combine them together and then we will get the answers from those models, right? So one example of this is the random forest. Another example is the XGBoost. So these are two different methods. One is the bagging based method, another is the boosting method. So let me quickly give very brief. So bagging based method and boosting based method. So what bagging based method is saying, let's say, just give you very brief. So what we do, we are creating multiple bags of data. Suppose you have data like this. So what we do, we will create parts of the data. Let's say I created 5 parts of the data. So one model is trained. So you can say model 1 is trained on this, model 2 is trained on this, model 3 is trained on this, model 4 is trained on this, and model 5 is trained on this. And these 5 models will give some result that we combine together. So that is the aggregation, and then you will give the final result, right? So what we do, if your models are independent in nature, there is no communication between the model, and they are dealing with, you can say, part 1 of the data, part 2 of the data, part 3 of the data, part 4 of, part 5 of, then this method is known as the bagging based method. We have created 5 bags of our data and we train 5 different models, and these 5 models will combine together, give you the final result. That is the bagging based method. While we create the model, we are not saying what other models are doing. We just create them independently. That is the bagging based method. What boosting is saying, here also, let's say we have some data. So first we'll take the P1 data, or you can say the data that we have. So it's like a complete data. Now we create a model M1 in the boosting. Then what we figure out, what are those places where M1 fail? M1 not able to give the correct answer. What are those places in our data where M1 fails? So what we'll do, when we create this P2, this data part of P2, we will focus more on those data where M1 fails. We will give lesser focus on the data where M1 has succeeded. So while we'll create another model M2 where it will focus more on those data where your previous model was failing. So that's why it is boosting the performance of the next based on the prior failure. And that's why it is known as the boosting mechanism, right? And one of the algorithm is the XGBoost here, the gradient based boosting method, right? So this is the way how we can make these ensembles. So why it is ensemble? Because here you do not have one model, you have multiple model. You have model 1, 2, 3, 4, 5. Similarly here also we will make multiple models. Only difference, or you can say that is the major difference. The difference is, whenever you create first model here, it is normal, no problem. But next when we create, we will say where your previous model failed, and we will give more focus on those data where your previous model is failing, and that is the boosting mechanism, right? So it is also known as the go-to model. What go-to model? Whenever you get some new problem, first you start with the XGBoost. That will give some good results. That's why we are saying it today's, for the structured data especially, it's a go-to model. You start with that. And we, as we are engineers, we all know about the Kaggle competitions and XGBoost winning multiple entries in the Kaggle competition. That's why we are lot focusing on the XGBoost, right? So as I said, XGBoost is something, so this is like a simple decision tree based method, right? Where you have some decisions here, and based on that you are taking outcome here and here, right? Similarly, decision tree ensemble, you have one decision, you have second decision. If they are independent in nature, then that is bagging. But if you say, no, what this decision tree has done, we will look into the failure. So here we have the failure. So we'll take a look of here so that failure will be reduced. So on the data where your first tree has failure, we will look into the next tree when these failure can be reduced. Right? So in that way we works in the XGBoost method. I hope it's clear. So in simple decision tree, so three things. If you say three things, one is the strong learner. Strong learner, where you have one decision tree, big decision tree. Just to take example, or you can say one decision tree is example, one model, one big model. Right? That is the strong learner. Then we have ensemble. In ensemble again we have two, bagging. Bagging where multiple models are there, but they are independent. They are not communicating together. So we create, let's say we have a data that we divided into multiple pieces, and each pieces look into, or each model look into their own piece only. That is the bagging method. Then boosting based method, we say we create first one, then whatever failure happen, we will focus more on the second one. Then whatever failure happen, we'll focus more on the third one, and so on. That is the boosting based method. Okay. Now, as I just simply, it will say tree 1. So we have the data set, we created tree 1. Where the error happened from the previous, then based on that we'll create tree. Where the error happened in tree 2, we'll create tree 3, and so on. That is the XGBoost method. Now let's talk about the data set, what we are dealing today, or what we are operating today. So we are using Backblaze dataset. This is a typical hard drive dataset. So this is coming from this data center. This is very big company of the data center. So what it do? They continuously taking multiple data from their drives. Maybe it can be RPM, maybe it can be the temperature, maybe it can be minute failure, and that is the time related data. Why it is time related data? Maybe every day they are monitoring these all information, right? So what we do, all of the drives, whatever available with them, they are giving a snapshot for a particular day, or the data, actually the data content, this contains every day snapshots of the information, right? So this is the way how we create the data, right? So let's see more on that data. So what the data contain? Of course the date, because we require the information day 1, day 2, day 3, day 4. So how we'll get date. Then we require serial number, which drive we are talking about, right? Then the model, the manufacturer assignment, or you can say what model of the drive. Then it has capacity as well in the bytes. Then failure column. If there is no failure, then it contains 0. If there is a failure, means last day the drive was failure, right? So that is the failure information. Getting? So these contain. Then along with that, we have lots of smart stats data, right? So total 90 columns of there, where one contain raw data and another contain normalized value, right? So total 45 different variety of data is given. Along with this, 5 data, we have this smart data, and actually this smart data is useful for us. This data is useful to create the data set for our application, for the learning. But once it is created, then smart data will help us to find out the failure, right? So now you can say that also there are, because this is a time series data, right? So there is a possible, there is a holes. What holes means? In particular day, data have not been recorded, and that day for that particular drive, that is the hole. So whenever we create the data, we will fill this hole with the help of forward filling. We'll use the technique forward filling to fill the data, right? So in this method, we will fill the data if you will find any holes are there, right? Or if there is a NA, then we also replace the NA. So these all we will do in the pre-processing, right? So what we will do, so if you say CPU using pandas for the data frame, that is first. Then what will you? We'll use GPU using pandas, and then finally we will train the XGBoost using rapids, and we'll see the performance, right? Now you can say what rapids is. Rapids is simply, you can say, the machine. So you can say, if you say scikit and rapids, let me put it here, right? So scikit plus numpy plus pandas, these all libraries for CPU. Scikit library, different variety of machine learning algorithms. That is, you can utilize the scikit and make the things, right? Similarly, numpy is there. Similarly, pandas is there, and rapids is useful for the GPU. Similarly, if you say numpy, so it's a cuPy. If you say pandas, there is a CUDF. So these all are doing almost similar job. Only difference, this is for GPU and these for the CPU. So if you have GPU in your hard drive, in your system, not hard drive, my bad. If you have GPU in your system, you can utilize this rapid cuPy or CUDF to run the operations on the GPU, and they are very fast in nature. Similar as the pandas library, their APIs are very similar as the pandas. So if you know pandas, understanding CUDF is very simple, very simple. Only thing, just you have to make your system ready for the CUDF, or you can say rapids. Just you need to install all those things, right? Only when you have the GPUs available. So that you can do later on as well. So how this rapids or CUDF works? So here you have lots of data. So you can say either you say data preparation or model training or visualization. Here we have multiple library. So for the data preparation, we have CUDF. So these all parts of the rapids. Within the rapids, you will get all these. You have CUDF, CUML for the machine learning things. If you have some graph analysis, you have a CU graph. Similarly, for the visualization, for deep learning, there are multiple methods in the rapids itself. So what they do, they are using Apache Arrow. That is the intermediate representation, so that you will get the booster performance, right? So in this way, the rapids are working. So of course, in fourth and fifth day, Nilesh sir will talk about this in detail, very detailed. Right? Then let's say how we'll compute the performance of the model. So there is a true positive, false negative, and true negative. I'm hoping we already discussed this yesterday, but let me do it again so that we'll just brush up the things. True positive means, in our case, what true positive means? If hard drive failure and that is classified as failure, right? That is the true positive. We also saying failure, our algorithm is also saying failure, and it is also failed previously, or you can say it is actually failed. That is the true positive. What is false positive? Your model is saying failure, but actually drive doesn't failure, it's working normal. That is false positive. We have to reduce the false positive. If you say we have very big system, and if you say okay, there is going to be failure, then you have to stop the system, check everything, that cost, right? So you cannot go with the lots of false positive. Then similarly, we have false negative. What false negative is saying? There are failure, but you are saying no, it's normal. Just go ahead. That is the false negative. So that also very dangerous, because that will create the fault. What is true negative? Your system is normal, and you are saying your model is also saying it's normal. It's a true negative. Getting? So this is the way how we'll compute true positive, false negative, true negative. So for us in this moment, the positive means the failure, right? The positive means the failure. If failed happen means some positive. Positive doesn't means like in normal positive means everything is good. But here positive is different. It is saying if failure happen, that is the positive. You have to indicate it, right? That is the positive. So you can think of this failure is similar as the medical application. When you say COVID positive, when someone have COVID, then you say positive. So it is similar. When failure happen, it's positive, right? So you can say failure, and you can say healthcare. When we say positive, means COVID positive means someone have COVID. So similarly here, if your machine is failing, then it's positive. Getting? So that you can easily relate. Positive means the failure. Similar as positive means the someone have some disease, then positive. Okay. So here we have some formulation, few more information related to this. Precision, recall, and F1 score. Let me give you few minutes here to just give you the details of recall, precision, and F1 score. These are very, very important, right? So in simpler word, how we can understand this precision recall? First we understand precision recall, then F1 score will come. So first we talk about the precision. What precision is saying, if you have given, let's say, let me give you example, ground truth of 20 positive, means 20 failure happened, whatever data is given to you, right? Now what you have done, whenever you do the prediction, you are able to find out only 10 positives, right? Only 10 positive which are matching with this, and you say 5 more positives which are not, which are actually negative, but you are saying positive, right? So means totally you are saying 15 positive. Out of 15, 10 are actually matching with this, and 5 are normal, but you are saying positive. So in that case, what will be the precision? So true positive you are getting 10, so we'll say 10, and false positive is 5. In short, you can say what all positive answers you have given. So let's say 15 positive answers you have given. Out of them, how many are correct? That will be the precision. Getting? So let me give you, so you can say totally you are saying 15 times your disk will fail. Right? 15 times your disk will fail. So 15 times disk will fail. That is your prediction. Right? In this prediction, actually 10 times it fail, which is matching with the failure, and 5 times it is normal, but you are saying it's failure. So out of given positive answers, how much you have given the correct positive and how much you have given the incorrect positive. So incorrect positive will come here. Correct positive means total positive is 15 that you have given. Out of them 10 are correct. So this will become the precision. Getting? So you have given total 15 positives. Out of the 10 positive are the correct. That is the precision. Now, in the beginning I said total 20 positive available in our data. Right? Out of 20, how many you are able to give correct? Only 10. So then here it will become 10 upon, so here 10, and 10 actually it was positive, but you have said negative. So it's a false negative. That will be 10. Getting? So then it will become 10 by 20. So this is the way how you'll identify false recall and precision. Let me give you one more example, then you will understand even better. Suppose you are going to the like you are searching something on the Google. Let's say you search for let's take example, you search for deep learning, right? You search for deep learning. Original record available in the Google, I said original record available in the Google related to the deep learning is, let's say, 10K. Just simplify. Original record this is available. But when you search it, it is giving 7K records. When you search deep learning, it is giving 7K record. But out of that 7K, 5K actually belong to the deep learning and 2K belong to something else. Right? So your system has given 7K records as an outcome, where 5K belong to the deep learning and 2K belong to something else. Now if someone say, can you compute the precision and recall? So how precision will compute? You have produces 7K results. So of course 7K will come into the picture in the bottom. True positive plus false positive. Total records you have given is the 7K. How many of them you have correctly identified as a deep learning? It's a 5 only. So that is 5 by 7 will be your precision. Right? Now in the recall, you will say total 10K was there, the original documents, which is belonging to the, you can say, belong to the deep learning. And out of that, 5 only we are able to get. That is the recall. It will give you a simplified version to understand the precision recall. Right? Okay. So in this way, you can give the precision recall. Now what is F1 score? F1 score is something which is harmonic mean of precision and recall. That is the F1 score. So when F1 score comes into the picture, let me take another example. And let me take the failure example so that you can easily figure out. Let's say failure example. So in that failure, let's say we have total 100 failure, right? And you are giving, just example, your model has given 150 answers. He has given 150 answers. And now let's take a case. Let's take a case. Here instead of giving 150 answers, so let me take the case 1 and 2, that will be better. Let's say 100 failure. That is the original. That is the ground truth, you can say. Now your model is giving the answers. Case 1, it is giving only one failure, one outcome as a fail, and that is the failure. When he is 100% insure, so you can say your bike is giving us almost black outcome from the engine and everything is almost damaged, and then you say it will be failure. Means you are 99.9% sure it will be fail, and then fail happen. So what will be the precision? You have given one answer and that one answer it failed. So your precision will become 1. Means only one time you say it is fail and at that time it fails. Then your precision will be 1. Now let's take another example. In case 2, you can say case 2, it will give 150 times fail. Means every time it is saying fail, 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 fail. It means total 150 records you have feed in and every time it is saying fail. And this 150 contains this 100 as well. That is the ground truth. So what that means? It is saying out of 150, what are the true positive? When it says fail, so it will be 100. And is really anything left out? No, it will be 100 only. So means your recall will be 1. So there are two extremes. One side, every time you say fail, 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 then your recall will become 100% recall, because you are not losing any failure. You are not missing out any failure, right? So recall will be 100%. In other side, whenever you are 100% sure there is a failure, then only you will say fail. So then precision will become 1. But none of them is good. Neither saying failure consistently is good idea, nor saying giving only one answer whenever you are full sure. So if you take them individually as a metric, then they are not a good idea. We want something where precision will also be high, recall will also be high. Then F1 score comes into the picture, where there encounter precision and recall. If anyone will down, your F1 score down. So then this F1 score evolves. That is the harmonic mean of that. Hoping it's clear to you. Now let's look into the lab, what we'll do in the lab. So first thing, we'll have these smart data every day. We will feed into the XG model, and this will say whether it is a failure or not, right? That is the in the training we will do. So in the training we have this label. So the training, you can say the training contain in such a way, you have this data, that is the X for you, and this is Y for you. And similarly such huge amount of data is available. When there is a failed or no failed, or you can say normal, both data is available. Normal data is also available, failed data is also available. So you will simply feed the data into the system, and label is available, that is failed or normal. And that way we will train this XGBoost model. Right. Now in the inference, what we will do, we will pass this data to XGBoost and check whether it fail or not. That is our inference. So we will find out whether it is normal or not, right? So now we are going only subset of data, because data is very huge, so that we will speed up. Otherwise maybe in the entire day we are ending with only one training only. So that's why we are taking smaller data, and we are using a simple model, not very complex model, to speed up the workflow, right? Now in the exercise you will find out this statement. So whenever you find this statement, you have to write your answer. I think you are already aware, because you have done yesterday. So whenever there is a to do, that we have to do. Okay, so these all things we will do. So we will use this D matrix to fit on the data. So, and we will use the denoising. We will use the different real data, that XGBoost will come into the picture, analyze the data, false positive, true positive, and all those things, right? So now let's jump into the model, jump into the lab. So here we will get the launch. 56 minutes. So what I will suggest, take next 5 minutes or 10 minutes and walk through the lab by your own first. Then I will explain each of them, right? First you walk through by your own, understand the things, and then we will explain in detail after 5 minutes. First you walk through it. So just one suggestion, while you walk through, make sure you are reading the text as well. So this text is important. So hoping you are visiting the lab. So hopefully you got a brief overview of the lab, what we are going to do in the lab. So let me give you a quick overview of the entire lab so that we can do it uh, very easily, right? Okay, so let's say start the predictive maintenance. So we already talked about predictive maintenance in detail in the slides. We will going to use this NVIDIA Rapids to uh, to solve the problem and few deep learning models in three labs, right? So some background. So we all know like while predictive maintenance is used to identifying the anomalies and little earlier to find out the anomaly. That's important, right? So why it is really important for us? So let's say that you can say the schedule based maintenance that we already discussed, like the problem with the schedule based maintenance and how we are able to overcome these problems with the predictive maintenance. So the predictive maintenance is something like when it required, we got to know little earlier and we'll do on the time, not before, not after. That's our target. If your predictive maintenance is 100% successful, right, then neither your system will break down nor you will do very early maintenance as well. So both sides it saves lots of money, right? So what we'll do in the lab, we will use this packed blast dataset, that is the hard drive dataset. So we will try to find out the failure in the hard drive in first section, right? In the first one, we'll find out the failure based on the one single record. We will feed one single record of that particular day or time. Then we will get to know whether the system will fail in next day or not, right? So that is first thing that we will do. That we will try to do in the lab one. We will feed record to the system and that system will tell whether your model will your drive will fail next day or not, means one single record. But we all know it's not just one day, right? It is like the system will indicate multiple days prior. It's not only one day like sudden happen. All the failure doesn't happen suddenly. They have some time. Some defect is coming slowly, some values are changing and then failure happen. So now to solve this, we are using the LSTM based model. What LSTM based model will do? They will take multiple days of data and then it will try to failure like when the failure will happen in advance. So maybe in 2 day advance, maybe in 3 day advance, depend upon the requirement, right? Then third, we'll talk about the anomaly detection in the autoencoder, right? In the anomaly detection, what we will do, so simply what we'll do in the anomaly detection, we will say we will have only good quality of data available, and if something wrong happened in the system, then we will try to figure out as an anomaly. And I will tell to the main person, or you can say the engineer or the plant manager, that something wrong is happening, please figure out. We'll not say it's a defect, but we'll say something which is not in the regular pattern. Then you will say there is anomaly, right? You can think, we'll talk about anomaly in the third lab in more detail, right? So now let's move forward. What we are doing here, we are simply importing the libraries numpy, pandas, system library, right? Date, time, shuffle library, random range, right? So these all libraries we are importing. So we all know how to run it. Just shift enter. Now we are loading the data set. What this data set contain? It contains smart statics data set as well. That also contain date, that also contain failure, it also contain model. So these all information contained in this data set. So we are reading from this CSV file, right? So now I am reading this CSV file, and first time it will take some time, right? So around 4 minutes to read. So we have to give some time to read the entire data. It's really big data. So that's why it is taking some time to read it. So in that, by that time it is reading, let's see what we'll get in our data set. So we'll get date, the date, where we'll say like date and time, serial number, model, capacity, as we already talked about. Failure, if it is 0, it's okay. If it is contained 1, means there is a failure in the last day. Failure in the last day, right? And then we have smart data, where we have 45 different smart stats available. And this is very important for us, right? Just waiting while it is reading. Because its data is really big, so that's why it is taking some time. Even for more detail related to this back blast, you can get it into this link, or it is also given here. You can go to this to find out the entire data. Okay, mean that in the meantime, if you have any question, please ask. Please put on the chat box so that you can take them forward. Oh, voice is not audible. Now is it audible? Can anyone confirm, please? Is it audible? Okay, fine, fine, fine. Thank you, thank you. Okay, so if you have any questions, please feel free to ask by the time this data is loading. You can type in the chat box. Any questions if you have in this session. Okay, so now data is loaded. Let's move forward. So we can see we have this data. So they have given smart data 1, then raw data, then normalized, then raw data, then normalized. And all these data is available here. And lots of NaN as well. So we'll, of course, we need to read off from those NaN, right? So just we are checking what is the shape of that data. So we have this much data and 95 columns that is available. And we have these much data available, right? So what we will do, of course, we already talked about that. So let's review some available counts. So these all the counts, like for this data, this is the count for this, for this, for this. So for the model, for different model, what is available with us in terms of hard drive, this particular drive has the maximum data. Maybe this particular model hard drive available maximum time. So what we'll do, because this is the most popular drive, so let's use this particular drive to train the model. If we go with the entire data, then it will take very long to train the system. So what we'll do, we will restrict our data into this drive, which is very popular. We can see here, this has this many records. So we'll restrict our training for this particular drive, and then we will train our model on this. So what we are taking this drive, and we are just compressing the data, or you can say not compressing the data, we are selecting only the data which is belong to this drive, right? So that we can utilize it for training. So this will just say, okay, if it is belong to drive, then your accordingly df will automatically updated. So once this statement will run, df contain only the data belong to this drive, other data will be gone, right? So let's run this cell, so that we will get only limited data which is belong to this drive. Now what we are doing here, if you see here, we are making the training data, and the test data, we are reading the test data from the directory test file, and we are keeping only the data belonging to this particular drive. If we'll say we will take all other drives data, might be our model will fail because they have not seen the drive information, right? Or maybe different drive have different behavior as well. So that's why we are restricting with the same drive on the testing data as well. Okay, so now once we done, then we are converting date and time format from the string, so that we can apply some operation on that. We are converting this string into the date and time format. Now the question comes, why we require date and time? The reason we require date and time, because we want to see date. The data is currently in the random order, it's not based on date, right? So what we'll do, we will simply say the data should be rearranged by date, so that we can say yesterday there was this data, so means tomorrow there can be failure. If you want to answer this, like yesterday we have these smart data available in the drive, and that will indicate tomorrow there can be a failure, so you need to store the data with date and time, then only we can answer. If it is a random order, then we cannot answer it, right? So that's why we are require date and time, right? Now what we are doing in here, we are getting just we are mapping the function, right? So that we will get a color map, a standard color map, that's it. So it's just showing the things, it is just to showcase the data, plotting the data and getting the color map, only those things. Now this particular function, if you check out this particular function will help us to remove something like range, right? Min max range or something, so that where we can figure out what will be the range, right? So that why we require this range, ultimately after some time we will do the normalization. In order to do the normalization, we require this range, so that's why we remove some constant and find out the range. Now here we want to clean the data, right? So in order to clean the data, as if you check out here, let me go back point. Yes, so let me go here. Here we can see like this is the smart data normalized, then smart data raw, then smart data again normalized, smart data raw, and then the way they normalize we are not aware. We want to normalize with our own way, right? So what we will do, first thing we will remove all those normalized column, and we will take only the raw data, so that we can apply our own normalization. We will not keep these normalized data, one thing, right? So that is the first thing we are going to do here, while we will say to update the data. So what we'll do, we will remove all the columns where we have this normalized value, right? So that's the way. So what we'll do, we will first find out the columns, right? And then we will remove those normalized columns, right? So one more thing, important point, if we remove all those columns, it doesn't have a valid data. How we can say valid data? Because they have any values. If they have only NA values available, means that is not useful for us. So we'll remove all of them, right? So this is the line which is doing this job. If there is a drop NA, particular column, multiple NAs, then it will drop, right? Just give me a minute. Okay. So what we have done, we first drop all the columns which have normal NA available. Similarly, we will drop those columns which have, so what we want to drop? We want to drop those columns if we have all NAs, not all NAs, that we want to drop the column, right? Similarly, we want to drop the rows, particular row which also contains some NA, right? So in that way, we will just remove all the NAs from the picture, right? Then what we have done, we will see, we find out what are the failure column. How we'll find out? We simply say when failure is 1, that is the failure data. So we divide it into two pieces. One is the failure data separately and normal data separately. So we have two pieces of data. One is failure, one is normal, right? Now, in order to get them some good value, we will say we will just find out the values here, then normalize. So we will remove this. So these all constant we will remove. Just when we say underscore raw, underscore normalize. And one more important, we will find out these columns. So these columns, you can see the columns that has date, serial number, model, capacity bytes, and failure. Once we will rearrange the data, so model, it's not important at all because we already restricted our data to one model. So means all the data contain only one single model. That doesn't have any importance. Serial number, every hard drive has independent serial number, doesn't have any pattern. Ultimately in machine learning we are figuring out the patterns, and serial number doesn't have any pattern. Maybe the way the serial number assigned, that have some pattern, but they are independent, they are unique for each, right? So that also doesn't have any information, no information related to the serial number. You cannot say this serial number hard drive is failing more, this serial number, if you make the serial number this, then hard drive will not fail. That doesn't make any difference. It is similar as, like you can say, if student name is X, then they will pass, but if student name is Y, they will fail. Doesn't make any sense, right? So that's why serial number also not important, because it contains all unique values. It will not have any pattern. Capacity, all of the models are same, so capacity is also not important. Date, once we rearrange the data on the date basis, after that date column is not useful. That's not useful, right? Once you rearrange, then it's not useful. For rearranging, it is useful, right? Now failure, that column is also not important. Why? Because we already created two separate data, if they are failed or not. So means if you have Y column available already in your training data, then it has one-to-one relationship. So that's why we have to remove the failure column and create two separate data here. One is the failed data, one is the normal data. So these all pre-processing we have done here to make our data suitable for the training, right? Still, if we have some NAs available, then we fill with the zeros, right? So let's run this cell so that we can do all pre-processing. So they have given the range, all the range of these data, all just what we have printed. Right? Now collecting the number of failed hard disk. Compare the distribution just to showcase. Right? Now we are just printing the histogram data so that we can see information from there, like how many datas in that length we are printing, right? So how many datas are there. So now we can see the histograms. Smart data 1, this is the histogram. Smart data 2, this is the histogram. Smart data 3, 4, 5. So these all histograms are there, right? So you can say based on this histogram you can figure out, okay, how data is distributed across the columns. You can say these data is very normal, this has like some values are very high, some values are very low, in that way, right? And this blue data is for the normal disk and this is for the failure disk. Now let's see the time series visualization. Based on the time, how it will be look like. So look at the time. So this bigger circle is the failure. So this is the time, x-axis is the time. So in the raw data 1, it failed here, it failed here, it failed here, and so on. In raw data 4, it failed here somewhere, it failed here, then this is failed here, and so on. So in that way you can see when the failure happened and which are the indicator of the failure, right? Now we are saving this pickle file, whatever we pre-processed, we are saving it so that we can utilize it later as well in upcoming labs itself. We do not need to do this entire pre-process again. We will directly use this pre-processed and we recreate the data from this pre-process based on the requirement of the algorithm, how we devise the algorithm, right? But raw data will be available here. So let us save it for future use. So this is what all pre-processing we have done on the data to prepare it and some visualization to understand the data. Now we already discussed the XGBoost. Skipping this part. So how we can do, like it's a tree 1, tree 2 and they have some errors. So overall how XGBoost works, the boosting method works that you have the tree 1, you have the data set, you train the tree 1, where it fails, you will give more focus on that data on tree 2. Where it fails again, it will give more focus on data where it failed, and so on. Similarly, we can create n number of trees. And whenever we will predict, we will say the outcome of this, outcome of this, outcome of this, and then we will take, or you can say we will simply aggregate the results to give the final answer. Now you can think like each tree are giving some answers. Let's say it's a classification where you say, like in our case it's a classification, we are saying failed or not. In that case what you can do, you can simply say first model is saying fail, second is saying normal, third is saying normal. What will be the answer? Simple, majority voting. Two are saying normal, one are saying fail, it means it will be normal, right? So in that way, you can give the majority voting and give the final answer in case of classification. But suppose you are dealing with the regression problem, where you are saying like some real values you have to produce. And let's say tree first is producing 10, tree second is producing 9, tree third is producing 8. So you'll take the average of that and say this is the correct answer. In that way you can deal with the regression. Okay, so now let's do the data preparation with the rapids, so that we will utilize it to train our model. We are just importing CUDF and of course XGBoost that we are going to use. So it is saying first thing, dropping unneat columns. What we want to drop? Model, date, serial number. That is not useful at all. So we are dropping all those information from our current data. So let's drop them. So once you say df.drop, and whatever columns you will mention here, all these columns will be dropped. After that, we are preparing the testing and training data. So separating training data features label. So you can say we have some training data for the failure, some training data for normal as well. Both are required, right? So we are taking the data for failure and normal. So separating training data features and label, test data features and label. What that mean? Features and label. Most important part, in the current data, we have all. We have failure column as well, right? So failure column means that column contain, if it is 0 means it's normal, if it is 1 it's a failure. So we just separate out that, right? So we have given this target, and that target is nothing, it is our label. Finally it's a label for us, that the target, right? So we separate it out, right? After that we just see, remove all the columns which are normalized, which contain normalized. If you here, the previous data we are not dealing with. Now we are creating new data with the CUDF. CUDF means with the help of GPU based library, and you can see how faster it is doing. Previously it was same thing, we are taking time, but now it is much faster, right? So in this moment we are doing with the much better way. So here we are removing all the columns which contain normalized, right? So normalized equal to -1 means we are taking all the columns which are not normalized. So what this line is saying, which doesn't contain normalized, we take all the columns. So that's why we have capacity, failure, smart 1, smart 2 and so on till smart 240. So these all data we have taken, right? So now it is saying remove 0 valued row. So what you will do? When an entire row contain all zeros, that we have to remove. Try to do it. Because if entire row contain all zeros, it's not useful, right? So we have to remove all the rows which contain only zeros. I just want to save myself for the typing. So it's simply say, find out the locations where they are not zeros on any axis and then take that data. Right? So we have all the columns, it doesn't have zeros. Any row which contain all zeros, that will be rid of. Now, why we are dropping the failure column? Because this is the label for us that we already taken. We need to drop this column. So we already taken label here, targets, the failure column. So we have this label available. Now we do not it. So we just drop this column. Now once we're done, then let's see how it looks like. Still we have capacity. Okay. So once we drop, it is going df train and df test. Df contain this information. So let's see. Let me take. So if you want to see df, so we'll say df. Okay, it's already dropped. So if you want to see only the train, so you can see the train which should not contain the failure. So now you can see we have capacity, we have smart 1, smart 2, smart 3 and so on. These all data. We have removed rid of the normalized data as well. And we have all this data available that will be used for the training. Now once we define the XGBoost, now let's say our data is ready. Now I want to one more thing, like you can see capacity bytes have all same data. So of course that will also be rid of, right? Now let's say we want to define our machine learning model, and that is the XGBoost. What XGBoost contain? What is the maximum tree depth that you will go? Individual tree, what will be the maximum depth? What are the tree method? It's a histogram based method. How many iterations you will do? 85 iterations. Subsample, regularization, gamma factor. So what is the role of gamma factor? Very important. Gamma specifies the minimum loss reduction required to split a node. What that means? It will tell you how much, if you split it, how much loss reduction is minimum required. If that much reduction is not happened, do not split. Suppose your gamma factor is 0.01. Just example. So what we'll do, we'll say if you will break the tree, if you will split the node, then minimum 0.01 loss should be reduction. If that is not happen, do not break it. That is the gamma function, right? So with this, so we have say already stopping 10 means in 10 iterations, if they are not improving, stop it. So now let's see the information. So here we have these all information related to the our system. So these are the Xeon processors that you are going to use, right? Now what we'll do here, we will start the CPU XGBoost and we will give all the parameters here and we'll train the XGBoost model and we'll see how much time it is taking. So here we say start time, time, and here we say time taken by the CPU that will be printed, and then we remove, or you can say delete all this information so that we will have free memory. Now what we'll do here, we are using D matrix. So the important part, we need to convert our data into D matrix. What D matrix is, D matrix help us, just important part, D matrix is optimized for memory efficiency, right? So the task that we are doing XGBoost, with the help of D matrix, we can do much faster with lesser memory, where this D matrix comes into the picture, right? So that's why we are using the D matrix to optimize for memory efficiency while you are training the XGBoost, right? So let's run this cell to train our XGBoost model. It will take some time to train the model. It's running constantly. So in this moment, we are using only pandas and we are using CPU library, that execute CPU library, to train the model. So this will also give a comparison. If you use pandas and GPU, how much time will take, that will do next. Here we are using pandas and simple XGBoost based model, that is the CPU based model, to train it. So it is taking around 55 seconds, around a minute, to train the entire model. Okay. Now, what next we are doing? Here we are not doing something new on the training or something new on the data preparation. Just we want to check while we are running with the GPU without CUDF, how fast it will be. Right? So we are using the GPU. So we are checking how GPU is available. Yes, you have 4 GPUs available, Tesla T4, and currently no use. So let's run this. So now what we are doing, we are simply running our model on GPU with simple pandas data frame. So what we do, the tree based, here you just say GPU dot underscore his, so it will train on the GPU. Comparatively faster, much faster, because we are utilizing 4 GPUs. So around 20 seconds, means almost like there was a 1 minute and this is 20 seconds, means around 35% of the time we are using. Now what we are doing, we are training GPU with CUDF, right? So what we need to do, first we have to create this training data and target into the CUDF format. So from pandas, we are converting into the CUDF, just one single line of the code that will convert from pandas to CUDF. So it load all in the CUDF. Now you have available this data into the CUDF format, and we train GPU with CUDF. And let's see how fast it will be. So you can see now time is reduced further. Now here nothing from the machine learning optimization side, like algorithm we are improving. No. Here the focus is comparison when you are using the GPUs, when you are using the CUDF, how much it impact. If you use only GPU, then it reduced, time will reduce. But if you use CUDF, you'll get very high performance. That is the comparison we want to show. So you can see if you are using only CPU and pandas, this much time, 55 seconds. If you use GPU, then it's a 20 second. And if you use GPU plus CUDF, you will take around this much time. Right? Now let's talk about the accuracy. Right? So here we have taken a threshold is 0.5 for the prediction. So if it is greater than threshold and less than threshold, accordingly we will do. Now here we have given entire test data. They say it's completed. Now let's compare it. Accuracy is almost close to, you can say, 99.99%, which is pretty good. But this is pretty good because of we have taken only one model of the data and testing on this same model itself. So we can say for understanding it's a really good idea, but whenever you run for all the data, then you will see the actual performance. Okay, so now we just want to measure, as I discussed, precision, recall, F1 score. So let's see. So just what you have to do not need to write all those formulation. You just say classification report, that is the function already available, and you pass your y true, the ground truth, and the target, the prediction value, and you will see what are the labels. So you'll find pretty fantastic results. You will say in the normal, almost F1 score is good, but in the failure, look at the F1 score. Precision is good, recall is not good at all. What that mean? It means they are able to give the answers whatever time they have given positive. 78% time positive was correct. But your model is not able to figure out all the positives. It was able to figure out only 3% of the positive from the overall. Normal is fine, they say all normals, but this is the most crucial. Then they are able to figure out the positives, right? So that's why you can check out, even the precision is good, but recall is bad. That's why your F1 score is also bad. And here F1 score comes into the picture. If this is good in both the places, then only F1 score is good. So here, why it is important? Because we are focusing on finding the failure. And overall, you can say your algorithm is not giving very good performance, right? Because out of 234, it was able to find out only 3% of the failure, not more than that, right? So this is some discussion to find out the details, how we can improve it, right? Summary of the data that we find out. So here you have training data is this, number of failed disk is this, and failed disk is what is the percentage. Just check out. That is the important point. It's only 0.8% of time it is failing. Getting? And similarly here in the test data, only 0.7% of the time it is failing. The failed data. What it indicates? It indicates you have huge amount of normal data, but you have very less data related to the failure. And what it indicates, this is not a balanced data. Let's give you one example. And that is the indication of this. That's why this precision recall F1 score comes into the picture. Suppose you are taking only accuracy. Just give you example why these are important. Suppose you are taking the accuracy and you have a data, because it's an imbalanced data. You have data. Let me take the let me take some space here. So it's good. Suppose you have 100 data points, right? In that 100 data points, 99 are the normal and 1 is the fault. And this is your test data that you have given to the algorithm. Now, if your algorithm is saying, let's say not, that's not a good idea. Let's say 90 and 10. Some bracket should be there, some space. Suppose your algorithm is saying, let's say it is all 100 times it's normal. Then what happened? Still your performance is 90% correct. But actually my focus is this, not the normal. But in here, if you say only 3% of the data that contains, so you can say if you have 100 points, out of 100, 97 are the normal and 3 are the fault. And if your model is saying 100, all 100 times they are normal, then also the accuracy will be 97%. So you can say my model is giving 97% of the accuracy, which doesn't make any usefulness. because of the imbalance in nature. Getting? So here F1 score precision recalls come into the picture. Out of 3, how many failure you detected? So in this case, if you say no failure detected, what will be the recall? 0. You are not able to detect any failure. Your recall will be 0. Getting? So that's why precision recalls and F1 score is important, especially whenever you have imbalanced data, right? So how to deal with the imbalanced data? What you can do, you can simply either reduce the data that is, there are multiple ways to handle actually, right? So what we are doing, we are sampling some data from the training and take the test data for smaller. So what we are doing, we are taking, let's say, only 0.2% of the training data and test data, which is normal, and complete test data, which somehow they balance. That's the way, that is one way. You are reducing the training data and taking the entire failure data. So reducing the normal data and taking entire failure data to handle it. Another way, you create some augmentation methods to create some failure data. That is another way. One more way is the weighting mechanism, where you are giving weight to the failure result and weight to the normal result in the loss function. So these are multiple ways to handle this. So here what we are using the sampling from the training data, and most data is, and all test data available. Or you can say all same, only sample from the normal data. How much? 20% of that, and we are taking complete failure data, so that we can balance out the things, right? So one question comes in our mind, if we take only 20% of the data, is really it is a good idea? Sometimes it's okay, but sometimes it's not a good idea. If you have enormous amount of data, still you are not utilizing it. That this particular technique is known as the downsampling. We have downsampled the data, right? Now let's take, once you downsample, how it impacts. So we are taking the data, that is downsampled data, and retrain the model. Right? So only for 19 epochs, because now we downsampled 20% of the data we are taking, so that's why it's very fast. And let's see the results, how good results we'll get. It's still improving. You can see the impact here. Here we are taking only 281 data for the normal and 234 all for the failure. Now it is improving. So this is one way to handle it, but always it's not a good way, right? So now this is the end of your first lab, and hoping you understand this first lab, because the knowledge of this first lab will be heavily utilized in upcoming lab. So if you have any doubt in the first lab, please feel free to ask. You can type in the chat. So it'll take next 2-3 minutes to answer the, if you have any doubt on the first lab, please. Any doubt on the first lab? Okay, so let us take a quick 10-minute break here, right? So it's 11:45. So we'll reassemble back by 11:55, and then we will jump to the next session, next lab. In the meantime, if you have, I'm available, I'm not going. So if you have any doubt, please feel free to ask. You can type in the chat so that I'll able to answer it. So I'm available. Others, you can take a quick break, and then we will jump into the next lab, next second session. Yeah, any questions if you have, please feel free to ask. Please type in the chat box. Okay, fine. So as Virendra asked, like, is it the better approach to augment data from more negative samples? Sometimes it's possible. You can augment the data with negative samples. And how it is possible, what you can do, we can create more data from the existing negative data by maybe by averaging it out, or maybe we can use some create some model to create more data from the negative data itself, right? And then we can augment it with that new data. Sometimes it's a good idea, but sometimes whenever this data is very crucial or it's very difficult to create new data from there, then it's always a good idea like downsample the another one, right? So what we can do, we can create a model. Let's say we have all old data, and we'll see in upcoming lab like autoencoder how we can create a model that will give the exactly same data as the outcome, right? So one way is like you can upsample the data, right? Upsample with the help of creating some new models or creating some statics based model, like maybe you can take the average it out, maybe you can create, or you can create a range of each data points and create the data in that range which is belong to that. In that way you can handle this. Okay, so in the meantime, next is the quiz that you have to do. Okay, so I'm not jumping in the quiz. It's your task. One more important information that I want to give, the answers that you are giving in the quiz, you have only 2 attempts. If you are failing in 2 attempts, it will not give you the marks. So let me give you the examples. So let me close this. So for example, here, so first quiz weightage is 15%. Second quiz weight, second is the coding part as well in the next lab that we will see. And second quiz also 15%. And third quiz is very important, which is 40%. So what even I have done while I was doing this exercise, I had made a mistake in one question, one single question. And because of that, 8% marks was deducted. So I just made mistake in one question in the third quiz, and because of that, that marks will be deducted. So you have to very ensure you do not make mistake more than twice, 1 and 2. In 2 attempts itself, you have to give the correct answer. If you go beyond that, then that question will treat as incorrect answer. So please make sure while you do the quiz, you have only 2 attempts. If you are confused, wait for it. Discuss it, then answer. And don't rush and give wrong answers. Otherwise, your certificate will not generate. So you have to pass it. Right. So here we have this. So once you are beyond this 90%, then only your certificate will generate. And now to get that, you have to pass this quiz. So if you are confused somewhere, don't mark the answer directly. First discuss, think on that. And the beauty here, all the answers are giving in this exercise itself. If you read the exercise properly, you will get the answers. Everything is here, right? So make sure you do it correctly, read it properly, then mark the answer. Okay, so we will be back. So we will start the session 11:55. So we'll take a break here. We'll resume at 11:55. So Priyanka, like just once you are like in the first task, you can directly close it. You do not have anything to submit here in the first task, right? And once you go to the next, automatically it will jump into the quiz. You can see it automatically jump into the quiz, right? So in that way, you can go to the quiz. Once you jump into the second task, then you will find a button here, SS task. I'll give the details, don't worry. So just go to the next, automatically it will go to the quiz. Just click on next. And I said, if you are confused, don't mark wrong answers. Okay, Deepak is asking, please explain accuracy of next question once more. Okay, sure. I'll do that. I'll do that. Okay, so let me take a blank space here to explain precision recall F1 score in a better way, or another example. So let me give the differentiation. Accuracy, precision, recall, and F1 score. Right. So I'll give the example. Instead of jumping into the formulation, I'll give you example. And example will help you in a better way. So I'll take example. Let's say we are, I'll take example of a rain. Just rain. It's a rainy season, or upcoming season is the rainy season. We are taking example of rain. Let's say we have 30 days. We are predicting for 1 month. Right? We have 30 days. Actually, in the ground truth, so let's say we are doing this prediction in the month of, so just we want to check our model. So of course, whenever we are checking the model quality, we should have original data available, ground truth available. Right? So let's say we are checking our model in the month of September, and we are checking on the August data, which is already done. Or let me do one thing, make it more realistic. Let's say we are right now, so April. So we have available April data, and today is the June. So we are checking today in the June. What that mean? These 30 days data belong to the April data, which we already have. The original data we already have. Out of these 30 days, just assumption, I know there is not rain for 10 days, but we are assuming 10 days was the rain. The rain happened on the 10 days. Of course, other 20 days, there was no rain. Right? So what we want, so this is the original data, that ground truth we already have. Right? Now let's say, so with that ground truth, let's say we have, so let me take a color, different color. We have model 1. What this model 1 is saying, it is saying, so first of all, we have given 15 days for prediction. Right? 15 days for the prediction. And these 15 days, let's assume these 15 days contain all these 10 days. These 15 days contain all these 10 days. Right? Means in the ground truth, there was 10 days when the rain actually happened. This 15 days contain. Now out of these 15 days, your model is saying 8 days rain happened. Means these are the positive answers from our model. From the model. Again I am saying from the model. Now out of 8, 5 was actual rain. Means this 5 actually match with this. Okay, so these 5 days actually raining happened, and remaining 3 days. So what you can say, these 5 days was true positive and these 3 days was false positive. Why it is false positive? Your model is saying these 3 days also rain happened, but actually there was no rain at all. Getting? So these will become false positive. Right? Now let's come to the accuracy. Jump to the accuracy part. Right? So accuracy will say how much like when the rain happened and when the rain doesn't happen, and your model is giving answers accordingly. So of course remaining 7 days is no rain, and we assume these 7 days, of course these 7 days contain some rain as well. So just to make the simpler, what we'll say, first I will jump to the precision part. I'm skipping the accuracy in this moment, I'm jumping into the precision part. So what precision is saying, TP divided by TP plus FP. So what it means, it is giving 8 positive. So now whenever we say positive, so we focus only on the positive. So total how many positive we have given? 8, which contain true positive, false positive. So 8 will come here. How many actually your model is giving correct? 5. So this will become your precision. Right? Now let's come to the recall. What recall is saying, true positive divided by true positive plus false negative. What that mean? It mean you have true positive is 5, so of course 5 plus false negative. Now let's think false negative. As I said, important part. So let me remove this line. As I said, these 15 days, contain these days as well. Contain these days as well. Right? What that mean? These 15 days contain these. So out of that, it is giving 8 days as a rain, and out of that 5 is the correct. So means remaining 5 days, it is giving false negative. It is giving false negative. So remaining 5 will come here, and that is the false negative. So what will be the answer? So in simple word, much simpler word, you can say this 10 is come here, and how many positive answers you have given, it will come here. Much simpler way. So 5 by 10 will be the recall. Now what is F1 score? So you can say it's a harmonic mean of that. So it's a 2 into precision into recall divided by precision plus recall. Is it correct? Okay. So in that way, you can easily figure out what will be the, so it's if I'm correct, this will come 2 into precision plus recall. So let me cross check, otherwise I don't want to give anything. Okay. So yeah, so that was correct. So this so this will not be there. Okay, and that way you can figure out. So just put the values on that and you'll get the answer. So this will not be there. So it's only 2 into precision recall divided by precision per recall. So in this way, you can find out the F1 score. Now let's come to the accuracy part. Accuracy will come true positive plus false negative divided by all, whatever answers they have given. So out of 15, how many true positive they have given? That is 5. How many false negative they have given? We can calculate, and that will be the accuracy. So in that way, you can differentiate precision, recall, F1 score, and accuracy. I hope this helps you. Yes, exactly. If you have higher precision, higher recall, your model is good. But higher accuracy, especially in case of imbalanced data, higher accuracy will not mean your model is good. Whenever we deal with the imbalanced data, imbalance means you have very less positive data and very high negative data. So means suppose as I has given the example, if you have 100 data points and out of 100 data points only one is the positive data, and then you are saying no, all 100 are negative, then also your accuracy is 99%. So means whenever you have imbalanced data, accuracy is not the good measure for finding your model is good or not. Then precision, recall, F1 score is the good measure. Especially I will say F1 score is the good measure because it's balancing both precision and recall. For more detail, what you can do, you can search on F beta score as well. So where beta value is 1, then it will become F1. More generalized F beta score, you search on that, and that will give you the control on precision and recall. How much you will give weightage to the precision and how much you will give weightage to the recall. So it will give the control, because in some application maybe precision is more important, recall is lesser important. So then accordingly you will set the beta value. In some application precision recall is more important, accordingly you will set the beta value. So that is F beta scores. You can search, you'll get the outcome. So hoping everyone has done the quiz successfully. And now let's move to the second lab. So let me download it so that I can use my pen. Great. Okay, so now, till now what we have done, we have used one data point at a time to predict the failure outcome. That we have done. Now let's see how we can use not only one data point, because we all know if you say some engine is failuring, some failure is happening, or some system is failure, it is not impact of just one day. This is more continuous in nature. Right? Lots of continuous things comes, then failure happen. It's not just one event task. Now what we want to use multiple days of data to predict the failure. And we want to predict the failure in more advance as well. Suppose you are saying no, predict the failure for tomorrow only. That is not always good idea, because maybe in one day advance you will not able to make the maintenance. Not possible. Some many applications. So what here we are trying to do, we want to predict the failure in more advance. So what we will try to do, let me take the pen. What we'll try to do here, we will say this is my model. I will feed here first day 1. So let me take the model here. So I want to create the model. I will feed here day 1 data, then I will feed day 2 data, then I will feed day 3 data, then let's say I will feed day 4 data and day 5 data. This I want to feed all those into our model. And then what I want from the model, I want that what will happen on, let's say, D7. What D7 means? 2 days ahead. What will happen? What will happen on D7? Is there any failure? So is failure happen or not on D7, right? So what we are doing, we are saying we will take this data D1 to D5 and we are trying to predict what will happen on D7. Maybe you can say D7 is not a good idea. I want D10. What D10 means? 5 days advance we will get to know that there can be a failure, so that we'll have ample amount of time to maintain it, right? So now the most important part, how we'll do that. So let's see, that is the entire lab focusing on how we will utilize this LSTM model to give you in advance that this failure can happen. And this LSTM model is also capable enough to take multiple days of data as well. Previously in XGBoost, if you say XGBoost, what we are saying, we will say D1 data, only D1 data, and it will able to tell what will happen D2, whether it will fail or not. That's the only thing we are able to do with the XGBoost. Now here in LSTM based model, what we are trying to do, we will give first D1, then give D2, then D3, then D4, then D5, a sequence of data, and based on these sequential pattern, we will find out what will happen on D10. That we are trying to do with the help of LSTM based model. Getting? So let's see how we'll do that. So that is the overview of lab. Again, we will use the same data, smart data, to train the LSTM model, right? And we will try to predict the potential future failure, right? Not like next day only. The current data, based on the current data, no. We will say LSTM will leverage series of data to look prior to the failure. That's important part, prior to the failure, right? So first thing, we will create the data and then we will try to optimize it, or we will create the LSTM model. So now we are in the lab 2, lab 1 we have done, now we are in the lab 2. So we'll talk about the recurrent neural network, we'll talk about the LSTM, we'll talk about the vanishing gradient as well. What vanishing gradient? That's why LSTM comes into the picture. And then we create the sequence of temporal data. That's very important, creating the data. It's very crucial. We'll see that how we'll create the data. Then we'll create the architecture, RNN architecture, and we'll again compare with the confusion matrix, F1 score, precision recall, and another ROC curve as well, right? So that will also come into the picture. So let's see. So first thing, how neural network, this recurrent neural network works, right? So before understanding recurrent neural network, first we need to understand how ANN works. that we have discussed in last day, in last uh, workshop. Yesterday we talked about the ANN. What we done with the ANN? We are feeding the data and it is giving the outcome, right? It is not taking the data for multiple days and then it will give the outcome. No, right? What it is doing, it is taking the data like in the previous lab itself, same thing we have done. We have given the data from one day and trying to predict the fault will happen or not the next day. That's maximum we are able to do with either ANN or maybe XGBoost or these models. Now here in the recurrent neural network, what we do, it's actually giving you the outcome in time series or sequential data. What sequential data means? So not only this, let's say whatever text we are reading. Suppose I want to understand the meaning of this sentence. I want to understand this. So if you will, I suppose someone will give you only this value. Can we understand the entire sentence? No. Suppose someone give only this value. Can we understand the entire sentence? No. Suppose someone has given jumbled value. Maybe first value is this, second is this, third is this, then fourth is this, then fifth is this, and so on. Then also it doesn't make any sense to us. It means in order to understand this sentence, we need this data in sequential order. And once we get this entire data, then we will say what is the meaning of that. Or you can say what is the understanding of that. It means lots of sequential data happens. Similarly, in our data, we are saying we have day 1 outcome, day 1 is smart data, day 2 is smart data, day 3 is smart data, and they have some relation in between. We are actually trying to find out those relation in between that is there, right? So we are using the recurrent network for that. What recurrent network is doing? Very important part. In summary, it looks like this. And if you expand it, it looks like this. So what this node contains? This is the weight matrix. We have already seen ANN that also contain the weights. This also contain the weights. Now you can see, so if you say the weights is W, so W is remain same in all the play time, right? So for xt minus 1, W is same, it will give some outcome. So you can say this is the feature is coming from here or hidden feature is coming from here that is required to understand the next word, right? So then second word, so in simply if you want to understand this sentence, so first RNN will go into the picture, then some information will carried out, then R will go into the picture, then created will go into the weight, then and so on, and finally once we done with the networks, it will give the outcome. This is my meaning of the sentence or summary of the sentence, whatever. Similarly here also what we'll do, we'll say day 1 data, of course it will give some hidden outcome that will go here, then day 2 data and hidden outcome will combine together, give some outcome, then day 3 data means understanding of day 1, then understanding of day 2, understanding of day 3, day 4, and so on. And finally, let's say we have day n data, and then it will say failure or not. And when we say failure or not, it will be little longer, right? So in that way, RNN works, means any sequential data RNN handle. Either it can be text data. Not only that, if you say the stock market data, that is also sequential in nature. Of course, tomorrow's stock price prediction, if you are trying to do, you cannot take only the yesterday. You can take yesterday, day before yesterday, and even last 1 week what happened, then based on that you will find out. That is also sequential data where RNN can be used. If you say weather forecast, it's not only the yesterday. Of course, the impact of yesterday is higher than previous, but impact is there. So we are taking maybe last 1 week was 1 month to give the prediction of tomorrow's weather. These all are sequential, right? So whenever you deal with the sequential data, you are using the recurrent neural network, not the simple artificial neural network. They are recurrent in nature. There are feedback. This feedback is important. Okay. So that is the recurrent neural network. Now, there is one problem in the recurrent neural network. Now, what is the problem? So before understanding the problem, one thing, here they are applying the activation. They are applying the activation. So in this node, if you say this node contain the weight matrix, and of course this weight matrix multiply with x and then apply the activation on the top of it. And this activation is the sigmoid. So I think yesterday itself we talk about the sigmoid activation, and the outcome of sigmoid we all know it is between 0 and 1, right? Between 0 and 1, what that mean? Once this S1 will come, this always will be between 0 and 1. Then S2 will come, this is also between 0 and 1. This also between 0 and 1, this also between 0 and 1, right? Now, even this information is not sufficient. In order to understand, we need to understand this WT, the gradient descent. WT is equal to WT, so you can say WT new is equal to WT old minus alpha, if you say delta L upon delta WT. If you explain this or if you expand this, what you will get? So now this is really important to understand. New equal to WT old minus alpha, and here it's y minus, so you can say y predicted minus y original, and here you have x of t. Now this x of t, for first layer x of t your input, but for the second x of t is not input. This is your activation here. For this is again your activation. Here this is again your activation. What that mean? If you look into, suppose I want to train, so let me erase some part so that it will be lesser messy. So suppose I want to train, let me take this. Suppose I want to train this time or this particular moment. So what will happen? Here you will take activation of this. So you can say activation of this, let's say here activation is A1, A2, A3, A4 and so on. So in this moment, what you will do, you will take this activation and this activation contain this also, multiply by this also, multiply by this also. Suppose this is very long, what will happen? So let me take this because it's between 0 and 1. Let's say 0 0.25, 0.2 into 0 0.25 into 0 0.1 into 0 0.6 and so on. What exactly happening here? What will be the value? If you have this sequence is very long. If you multiply by, let's say 0 0.2 into 0 0.25, what you will get? 0 0.045, right? Or 0.5. So you will get, if you take here 0 0.05, what that mean? It reduced. Again you multiply by 0.1, 0 0.005. Again you multiply by 0.6, it further reduce. So what will happen till it reach here? This value, so the value that is here, this value, this value will reduce to 0, close to 0. And if this value is what is multiplying is close to 0, what will happen to the update in this weight? It will be no update. And this is the problem of vanishing gradient. Hope you understand. This is the problem of vanishing gradient. Your gradient is vanished till it is reaching the initial layer. Why it is vanished? Because in this place activation, this place activation, this place activation, this place activation, and all activation is giving between 0 and 1. So if somehow we will make a line that do not have any activation and reach to the next layer, then once you go back, then your gradient will remain there, and this is what LSTM is doing. So let's see how LSTM works. So you can see vanishing gradient is saved by this line. So let me take different color. so that we can highlight it. So you can check out this. This line doesn't have any activation. It has multiplication, it has addition, but do not have any activation. Means the value which is coming from this cell will not multiplied by between 0 and 1. It will remain similar. And this cell is going back, back, back. Means your gradient will be remain till beginning itself. And that's why this LSTM comes into the picture. This line will help us from the reducing vanishing gradient. Then here we have multiple gates. This is the for gate, this is the input gate, right? So these all gates are there. So that is the role of the LSTM, that it is taking multiple, it is able to understand in the long run. And how they understand? Because of the reducing the vanishing gradient problem. So here you have output gate, here you have input gate, here you have the forget gate. What forget gate is doing? So forget gate means there is one network here, one network here, two networks, one network here. Means these weights are trained, and these weights are, so for example, let's take these weights. These weights are trained to give the information on this cell line. This particular word or this particular information is important or not. If it is not important, then that information will multiply by close to 0. And if it is important, that will be multiplied by close to 1. Because here it is giving sigmoid. So what sigmoid is doing? If the information that is going here, if it is important, then it will be multiplied by close to 1. So your this fully connected network will give outcome in that way, so that it will give close to 1, and that will be multiplied in the line because that is important. And if it is not important, it will be close to 0. And again, this is the responsibility of this fully connected layer. Like so you are training itself in a way so that they will understand this word is important, this word is not important. If it is not important, it will not add up anything here. So this way it trains. Then you have input layer. So how much input is important, and then accordingly it will be added. Then output gate based on this cell. So again, output is also contain this cell. Output gate will give from here, and this will give the output. So that is the LSTM based model, right? So this is used in many places: speech synthesis, speech recognition, right? And many other places as well. Whenever you have sequential data, LSTM is useful. Audio, video analysis, these all handwritten character recognition, sequence prediction, right? So these all able to handle by the LSTM. Now in this lab we will apply LSTM to solve our problem, this failure problem, right? So how it works? So what we'll do, we will create LSTM in this way, x1, x2. In this moment, these are the same LSTMs. It is not like we are creating 4 different LSTM. No. These are like time 1, time 2, time 3, time 4, and so on. So one LSTM will take x1, give the output, then same, take the x2, then give the output, take 3, same, give the input and take the output, and so on. So these LSTMs are the same, right? It will take the data one by one and give the output. But we know if we go with this is very simple in nature. It will not able to handle multiple problems. So what we do, we make the stacked LSTM. How it works? We have multiple. So in this case, what you can say, if you say LSTM 1, so this will be 1, 1, 1. This is 2, so this will be 2, 2, 2. This is 3, it will be 3, 3, 3, and so on. So this is the way we are stacking multiple LSTMs. So this is the stacked LSTM. Suppose you are saying, no, here in this we have 128 nodes. So LSTM 1, 2, 3, and so on, 128 LSTM nodes will be there. Then next layer again, so on. Okay. So in that way, we create the stacked LSTM. Right. Now there is a CNN as well, where we are using the CNN to get the features. So we have seen last time, CNN is nothing, it's a feature extractor. Now the question will come, how we'll use CNN for the time series, right? So in order to use the CNN for the time series, we will use simply 1D CNN. What we'll do, we will use 1D CNN, right? So how this 1D CNN will work? We'll say, let me take, so this CNN will work in this way. Suppose I have CNN, it is 3, because it's 1D CNN, it's 3 cross 1. In this case, it's a 3 cross 1. So then it will go on this, then it will move in one direction, go on this, then again it will move one direction, it will go on this, and it will produce the outcome. That is the 1D CNN we will use. So these are the CNN. So here these are the CNN. So what this 1D CNN will do, it will produce the outcome in 1D, because it is going in one direction only. So this 1D CNN will come into the picture while we are dealing with time series data. Time series, simple tabular data. Time series tabular data, then 1D CNN will come into the picture. Now you can say, if you have videos, then of course 1D CNN will not work out. 1D CNN is good for time series, but for tabular data, one dimension, right? But suppose you have videos, then 3D CNN comes into the picture, where the third dimension of this is the time. How it works? Let me give you an idea. Suppose this is your first image, this is your second image, this is your third image, this is your fourth image, right? Now what you will do, you will take first CNN here, then so you have 3 direction to jump. One is this, one is this, and one is this as well. And that's why it will give 3-dimensional output. So once you say this direction, it is the temporal direction, where you say in the first frame what you have seen, in the second frame what you have seen. So first it will go this, and then it will go to the next frame. That will give you what we are getting in the videos. Getting? So that is 3 dimension. That is also handling the time series, but more on the image related data. But whenever you have simple like the current data that we are dealing, that is 1D CNN is good, because it is also moving in one direction. That so this direction is nothing, it's a temporal direction, time direction, right? So that we are doing. So that 1D CNN will utilize to solve the problem. So Keras, we have lots of libraries that we are going to use. So how simply it will be look like, we already seen yesterday. So I'm hoping this we are already aware. So instead of giving a lot of time to this, let's jump into the next. Because in the yesterday lab, we have seen all these statements. Right? Now, this is important. What we want to do. What do we want to do? We want to find out remaining useful life. Right? So what we are doing, we are saying we will give this data and we are predicting what is remaining useful life, means the failure, right? So let's take example, just giving you example. Suppose you have data, of course we know we have data from D1, D2, then let's say we have D20, D30, 30 days data, right? Now in this series, let's say D15, there is a failure. Just example, there is a failure on D15. Now suppose you want to identify this failure 10 days ahead. How much days? 10 days ahead, right? So in that case, what you will have, you have D1 to D5 that you will feed D1 to D5. Here you will feed D1 to D5 here, and outcome that you will give of this. Getting? You will feed day n to day 4 and you will give outcome of this advance. So in our model, what you will give, in our LSTM model, what we will give, we will give D1, D2, D3, D4 and D5, right? and the outcome that it will give for if you want 10 days ahead, just example 10 days ahead. So we'll say what happened on D15 outcome. So there was failure on D15, so that's why we will, once we'll give data D1, D2, D3, D4, the outcome should be failure. Now D16 we do not have any failure, so then what you will give, once you will give D2, D3, D4, D5 and D6 to the same LSTM model, it will give D16 output, and that output of course normal. So in that way we will create the data. So what it indicating, if it is failuring on D15 means what is remaining useful life, 10 days remaining useful life. Getting? So for example, it is moving here and giving some outcome, so automatically you can say what is the remaining useful life. We want to identify 10 days ahead, so 10 remaining useful life. Suppose I want to check, okay, whether it will fail in next 20 days. So then accordingly we will prepare the data, right? So that's the way how we'll prepare the data, which is very crucial for our second lab. Okay, so let's move forward. So as I said, how we'll do that? We will say this is the S days. So the data is this that we will take. So drive over S days data and how much advance we want, that is L days advance. Just to simplify. So if you take it in our example, S is nothing. We have taken S equal to 5, right? And advance L equal to 10 days. So that will give the 10 days ahead. Is there any failed or not? So in that way we will train the model, and once we test it, what we will give 5 days data and model will say whether it will fail or not in 10 days ahead. So what we will do in our application, we will take 2 days ahead or 3 days ahead. So in that case we will take 5 days data. So in summary you can say we will take, so you will say we have day 1 to day 5 that will feed in into the system, into the LSTM model, and it will say what will happen D7, whether there will be failure or not. Right? So in that way we'll create our data. So hopefully you understand how to create the data. Same thing we will use for convolution as well. In the convolution we will use the similar kind of data, only in place of LSTM we will use 1D convolution. So it will say your convolution is going like this, in this way. So it will move towards this direction and give you the outcome. Getting? So that's the way how we'll do. So let's move forward to the lab. So here our lab is started. Now here you should ensure there is a task that we have to do and then assess it, that we need to ensure. So let me launch this. Okay, so let me quickly walk through. Okay, because this lab is little longer and lunch break is coming soon. So what we'll do, we will go for the lunch break and we'll be back. So it's 12:40. So we'll back by 140. It's a 1 hour lunch break. Or take it little smaller, take 40-minute lunch break. I think that will be good enough. But what's your suggestion? 40-minute will be good enough? Okay, great. So we'll take 40-minute break. So we will come back around, let's take 1:30. It's a good idea. So we'll resume 1:30, and as soon as you come into this will just create. So this particular column will be created, or the data will be created, but initially it is with the NaN. So this part will just create the space for filling the data if the days is missing. And this forward fill will help us to create, or you can say to fill that Na with the help of forward fill. Forward fill means suppose 17th is not available, 16th is available, so 16 data will be copied or filled to the 17th. That is the forward filling. So this is the role of this particular function. So let's run this. Now here we are fixing the date gaps. So we will find out what the gaps are there and we'll try to fix it. And of course, after the fixing, we will reset. So you can see the functions what we have created here, adjust date, that is called here, and then we will fix it. So once we find out, okay, there is a space, then adjust date function will call, and that will fix the information. Now here we are creating the failed sequences. So just simple routine to create the failed sequence, right? So what we'll do, we'll say suppose, so you can check out, let me zoom it little bit. So you are saying going back, how much look ahead we want. Suppose you want 2 days look ahead. So what we'll do, and how much data we are feeding, let's say I'm feeding 5 days data and looking ahead for 2 days ahead. So what will happen, we'll say if you check out the failures only, suppose we are checking only the failure. So if the failure happen on 7th day, so for getting that outcome, we have 1 to 5. Suppose failure is happening 10th day. So then what will happen? If it is 10th day, so then 2 days ahead. So means you have 8 to 3. 3 to 8 will be the required things, right? And that will give you the 10th day failure. So in that way, you will find out the ahead. So how much ahead we are looking forward, right? So we are creating, so that's why here we give the data frame to create the sequence length. You want 5 days data, 6 days data, 7 days data. That's why we create more generalized function. So here you give the sequence length and look at how many days you are looking ahead. Suppose you say no, I want 6 days data and I want to look ahead for 3 days. So automatically this function will create the sequence accordingly. So if you want to say 6 days, so you can say your first data frame will be 1, 2, 3, 4, 5, 6, and look ahead of 3 days. So it will be going for the 9th days. So 9th day outcome will be your actual outcome, your label, right? So in that way we created the failed sequences because we separately created the normal sequences, separate failed sequences, but processes remain same. Only thing, because we have separate the data for failed sequences, separate one section, and separate the data for normal sequences in other section. That's why we creating with the two different methods. Otherwise, both of them are doing the similar job. So either you say create failed sequence or create normal sequence, they are doing the similar job. Okay. Now, what next? We are inserting the labels. Labels, it is the failed or normal. That's the label sequence that we look forward. Whether it is the failed or normal, that will be added. So now here you defined what is the sequence length we want. We want 5 days sequence length. How many look ahead? Only 1 day look ahead. Means 1 day prior. Number of normal disk 20. Number of maximum normal sequences that we want to create, that is 4000. So these many sequences we want to create, right? So let's run. So now parameters are decided, and here we will create the entire data that we have used. So all the functions that we created, we will utilize here to create the sequences. So you can say create normal sequence, create failed sequence, right? And you can say fix the date gaps that we all discuss, get this serial number, and all these will be done. So what functions we have created, we will utilize and create the samples. So you can say when you create the training sample, finally we are concatenating both normal sequences and failed sequences together, so that our entire training data will be ready, which contain normal sequences as well and failed sequences as well. So if you just want to see how the data will be look like, it will be look like this. So it's still running. So let it run. Then I'll get outcome. Okay, by the time it is running, if anyone has any doubt, please feel free after completing this old question. Anyone, any question here? Please feel free to ask. Total 4,000 sequences created. Number of failed sequences created 1061. Okay. So now here we have seen the data. So you can say this is first sequence 0, 1, 2, 3, 4. That is the first sequence. Second sequence 1, 2, 3, 4, 5. So these are the sequence, means one data actually looks is combined together. So you can say one data point in your case is 0 to 4, the entire data and the label. That is one data sequence. Similarly, another data sequence is 1 to 5 and the label. That is the another data sequence, right? Similarly, what is the first? Just you can check. So this is your one data sequence, which is failure, right? So in that way, we created failure sequence. So here, this failure column is not important for us. Why this is not important? Because this is not we are going to predict. What we are going to use, we are going to use this smart data. So these values, like these all values will feed first time instance. So first data will go, then second data will go, third, fourth, fifth. After fifth data, we will do the prediction, right? So in that way it works. So just we want to just see how many days we look forward, and we will see like the details when the failure happened. We'll see this is the failure we figure out, right? So that is the first failure happened in our data, right? Now we are checking how many samples we have, right? So we say these many samples required. So these many normal samples, total samples are there in the training samples, which includes failure samples as well as the normal samples as well, right? So now with that, let's move forward. So what we have done, because the current is very huge in nature, so we are going to store the data into the pickle file and clear the memory so that we can move forward. So just we are storing the data into the pickle file, and then we will move forward so that we can save some memory. Okay. GC is nothing, it's just a garbage collector that we are calling explicitly, right? So we repeat the same process for test data, same way as we created the training data. Of course, test data also require the same thing, so we repeat this for the test data. So let's run so that we will have test data, and we also store it into the pickle file and do the garbage collection after deleting this. Okay, now let's do what we are doing here, creating X and Y label. Till now, once you say sequence, sequence only contain the X. It do not have, till now, it do not have Y, right? So what we'll do, we are taking the sequences of train and test, and then we will create the label. So let's read this first of all. You got this. Now here the question comes, there is a serial number, right? And there is a failure. Do you really need this? And same, do we need the date column? Because we already created the sequences. Now we do not need either date column, neither need the sequences, serial number, not we need the failure as well, right? That is not required. Why it is not required? We already discussed. Because for training, we cannot use the failure column. For training, date is also not useful. For training, serial number is also not useful. That's why we are removing. So now here they are saying you have to use this to do section. You have to create for the X train and Y X test. So how will get X train and X test? So in this moment, if you just think on, just give you a hint, till now we are using the pandas and this contain the data with these names. Now we do not need names. We need only the values because we are not feeding the names on our model. So here you can simply say X train is equal to df.train dot values. We are looking only for the values. We are not looking for the data frame. We are focusing on the values. So here we require the values only, right? Same thing can say we have to drop the column and take the values. So here we need to drop these columns from our data. So dropping which column? Date column, serial number, failure, sequence number, because these all are not important. So dropping this column. Y train, of course, the sequence label that we have. Right? Now what we are doing, we are simply creating or we are pre-processing and we are doing the normalization now. So we are using this in simple standard scalar normalization and then we normalize our data. Because we have not used the normalized column because previously they normalized by their own way. Now I want to normalize with the standard scalar function, right? So we just normalize this. So what we have done, we have taken these values. As I said, we need only the values. We are not thinking on the data frame. We need only the values. So we have taken the values in the X train. We created a scalar function for the pre-processing, right? And then we transform it. Right. Similarly, we have done the transformation for test as well. Right. So simply we have done the transform means we normalize it and run the things. Right. Now what we want here, we want to reshape the training data. Right. So how reshape means currently the data is available in all sequence because we want to feed into the LSTM the three-dimensional data required number of samples, timestamps and number of features. Timestamp means 5 sequences that we are talking about, 5 timestamps. Number of features, how many columns we have, and total number of samples. In that way, we have to restructure our data to feed into the system. So what we'll do, let me take this. So instead of, so what you can check out, I'll do that. What we have done. So we simply use the number of sequences, total number of training data that we have, and the sequence length. That will give the number of instances that we have. Sequence length, we already know, it's currently we set as 5. And shape, that is important. What will be the shape? In this moment, the shape will be the column, how many features we have. That is our shape, how many features we have. So X train dot shape one, that will give the features. Similarly for the test. So let's run this cell. So previously this was given like this. So we have 24 features and these all data. Now we converted into the sequences. Right. So total number of sequences 5041, which include failed sequence as well as the normal sequences, right? That we created. Okay. Any questions so far? So till now what we are doing, we are just creating the data in this moment, right? It's a data preparation that we are trying to do here. Consistently we are doing the data preparation till now. Now our X is ready, right? And so what we are doing, y train. So we are giving y train dot values and what sequence length, whatever we have given. So that will be our y train value. Similarly here, so let's run this cell so that we will, what we'll do, we will create a y label, failed or not, both on the test and error. That is the last column, y train or y test. Now we want to design the model, that is the stacked LSTM, like this. So you have LSTM 1, 2, 3. In that way we will create the stacked LSTM. So now let's look into that, because your exercise is looking for this model section. So once you go to the exercise, they will tell you to create the model for this and this way. So you have to understand this very well so that you can do it in the exercise. So what we have done, so let's see. So first we have import the sequential from TensorFlow Keras, then imported the LSTM layer. Here we have DP level, that is the dropout, and I'm hoping you know dropout from the previous study. We discussed the dropout. So dropout is helping us to reduce the overfitting, right? So dropout is one kind of regularizer that we use to reduce the overfitting. So how dropout works? A quick overview. Dropout simply whenever you will train the model. So whenever your model is coming backward, back propagation, and if your dropout is 0.2, so means 20% of the nodes will not participate on the training. What that means, these nodes will not update their weights, and these 20% node will be randomly selected, right? So that is the dropout level. Now here we have regularizer level. This is simple L2 regularization that we already know, the L2 regularization. So that we are going to use. Number of units 64. So we predefined it's a 64 unit that we are going to take. Means your LSTM, 3 LSTM layer, and each layer has 64 nodes, right? So how many layers we created? 3 LSTM layer. Every layer has 64 nodes. First layer has additional information, and what is that? You have input shape. What is the input shape for us? Is 5. So what will be the input shape for us? It will be 5 cross. So it will give 5, and this will give how many features you have. Correct? Number of features. So if you take out here, this is coming into the picture. 5 cross 24. I'm correct? So here we have 5 cross 24, and this 5 cross 24 means, so because it's, if you say X train shape 0, so that will give you how many sequences you have. But in the input we want length of sequence, each sequence. So that X train dot shape 1 will give you length of sequence, that is 5. How many features in each sequence? That is given by X train dot shape 2. Just keep this in mind. That will help you, right? Now we have used the dropout here, dropout level, DP level, recurrent dropout in the recurrent layer, that is DP level, and here we have return sequence is true. So when your next layer is again LSTM layer, then return sequence is true. When next layer is not LSTM, it's fully connected, then return sequence will be false, right? So because the next layer we have again LSTM layer, here it's, we do not need input shape, because this is the output for second layer is coming from the previous LSTM layer. So it doesn't need an input shape here, right? So we have directly number of units, dropout, recurrent dropout, and return sequence is true. Why true? Because next layer again it's a LSTM layer. So we have taken third LSTM layer, units, dropout level, recurrent dropout level, and return sequence is false. Why false? Because next what we are going to use, that is not the LSTM layer, we are going to use the dense layer, right? Because the dense layer will give you the outcome, final outcome, that true or false, failed or not failed, right? So if you say my answer is failed or not failed, so last answer is just one outcome, either fail or not fail. So last layer node is 1. But before that we have taken one more layer, model dot add dense, and we have used activation function tan h, and activity regularizer is L2 regularizer here. So we use activation regularizer here, that is L2 regularizer. What activation regularizer will do? It will try to make your activation sparse in nature, so that your model will not overfit, right? Now we add a dropout here, of course, dropout. So here we have added a dropout, that is 0.02. Then add a dense layer. Again, it's a units. How many units we have predefined? It's a 64 units. So 64 here. Activation is tan h and activity is this. Now finally we have added a final dense layer that has one node, and this one node will give you the outcome. The outcome, because it's a tan h activation, so you can simply say if it is a positive, because tan h range is -1 to 1, so if it is a positive, 0 or positive, then you say it's a positive answer. If it is a negative, then it's a negative answer. So simply we can use one node that will give indication whether there is a failure or not. Anyone, any question on this part, model creation? Any doubt? This is really important. Okay, so now let me run this. It created the model. Let me run this as well. Now it added. Even what you can do, these 3 lines, so these 4 lines and these 4 lines you can write together. There's no compulsion it should be 2 different pieces. No. If you will copy these lines and put it here immediately after this, then also it will work in the same way. Similarly, we will do in our exercise. Now we'll check the model summary. So you can see what input layers, 5, 64. Okay. Then here we have LSTM layer, then again LSTM layer, it is giving the outcome. Then we have final one node is here. Ready? So in that way we will get the outcome. Okay, now we want to train the model. So let's run this cell. So what we have done, we have given 50 epochs to train it. Learning rate 0.001. Learning rate decay we have used. So after every epoch, it will decay the learning rate. And that decayed learning rate will be utilized here. So we can say decay learning rate is here. So your ADAM optimizer will use the decay learning rate to perform the task. Right? Then we compile the model with the optimizer. What is loss? Binary cross entropy loss. Metric is accuracy and MAE. Both metrics we are utilizing. And we have used the checkpointing so that best model will be saved. So let's run this cell. It will take some time to train the model. Okay, by that time it is training. Let me go down where we have the exercise. So now, because we already have the information available, what they want here in the exercise, they want to create a model where the prediction is not one. It's not failure or not failure. What they want to create a model where we will give these 4 features and fifth day features will be predicted. This will be the label. So what they want fifth day features should be your output. It will be your output of the model. So of course, where we are saying dense 1, it will no more dense 1. What will be that? Number of features. And from where the features are coming? If you say X train, shape, and the third index, the 2 index, that is giving the features. So of course, the dense layer, what number of values will create? It will be the fifth layer, third values as a outcome. Now along with that, what they want, so they say in order to create the model, what you have to do? First, you have 2 stacked LSTM layer. Means how many layers you want? 2 layer. First layer contain the input and other parameters. How many units? 128 units. Last layer output, what they want? So such as two stack. So of course, one will have the input layer, second will have the again 128 unit, and return sequence will be false in the second layer. Getting? Now what we want, so last or second layer LSTM output will go to the dense layer as we have done previously, and this dense layer has 256 nodes. So you will create one dense layer that contain 256 node and activation function is 10H. After that, fourth layer you will create a dropout layer that has 0.2 per dropout value. Then next, we will create another dense layer that has output 128 unit and 10H. So one more layer after dropout that has 128 unit and 10H. And last layer, we will create the output layer equal the dimension of single row data. Single row data means one single row, how many features you have. You have to figure out from the training data that you have to create. So what you will do, how will do this exercise? Once you click on that, it will open here and just you have to create the model in this part. So let me zoom out. You do not need to touch anything here, just you have to create the model in this part, to do part. So what you will do, first you create LSTM layer, second you create LSTM layer, third you create dense layer with 256 unit, fourth you create the dropout layer with 0.2% dropout, then fifth you create again dense layer, then sixth you will create a dense layer with the equal number of unit that is based on the X train feature value. How many feature values? X train dot shape and the 2 index. Getting? So in that way your model will be created. So this will help you in the, because you just now we talked about all LSTM model. So that's why I want to give you the information of the assessment. Once you do that, once you create the model here, you have to save with Control S, and after saving you have to go down and run this script. Once you run it, it will give you information, your that assessment score. If it is 1 means 100% correct, if it is 0, there is only 1 and 0. If there is something wrong you have done, then it will give you 0. Till you are not getting 1, you cannot go back here and assess the task. Okay, so some information, so we'll come back this information again. So hopefully now by this time our model okay, so our model has been created. Now we fit the model. Now model training is going on. So by the time this model is training, let's try to do this part. so that we can utilize. So what you can do, where model we have created, you just take this information from this and copy, and of course delete this and paste it here. One important thing, we required only 2 layers, so of course this layer is not important for us, so we can delete this, right? Now input shape, that will remain same, whatever inputs are coming, it will remain same except 1, except 2. Dropout, now here what change they look forward? Units. How many units they want? If you check out here, how many units they want? 128 unit size, right? So here you have to make this unit 128. Similarly, another LSTM also want 128. Make sure these recurrent sequences should be false, because after this we are going to add the fully connected layer. So this should be false. So they have already given DP level 0.2, regularizer is 0.002. So we do not need to worry about these values. They are already given. Now what next we have to do here? We have to add the fully connected layer. Right? So how will add the fully connected layer? You already know it. So these are the fully connected layer. We can take this completely, so that whatever not important, we will remove it. So make sure the indentation should be correct. Otherwise, your model will throw error, right? So here, how many number of units they look forward? 256 units. You can check out. So how many units they want? 256 unit and 10H. Then another will be the dropout layer. So after this, they want dropout layer, which we already have. The next, they want to add one more layer, that is 128 layer. So we will make this 128, and this is very crucial part. As it said, if you go back, as it says, output will be number of features. And where is number of features here? In this part. You'll get the number of features. That's it. You have created your model. Right? So just give you a hint how to do that. Hopefully our task is done. Still going on. Anyone, any question if you have in mind, please feel free to ask. I have, Shriyans, I answered your question. Yeah, I will do that. Okay, so I'll do that. Once I'll finish this, then I will again explain how to do the assessment part. Okay, so now we have done our training part here, right? Now we will go here and check how good is our performance. So this is your training accuracy and this is your test accuracy. Doesn't look very good, of course. So now we want to just evaluate the model. So we are loading this model and we want to evaluate it. So let's run this. It evaluated the model, and finally what we got accuracy is just 65%. It's not very good. So of course we have taken only piece of the data, only 20% of the data of even one single day. So that's why your performance is not that good. But this is the process. So important part is to define the process. So now here we have taken false positive, true positive, false negative, true negative that we already explained, recall, precision, F1 score, and we want to check the report. How good is our model is. So we found again, so in case of precision, 96% precision on the good sequences, and bad sequences precision is not that good. Similarly, recall on the good sequences is bad, but recall on the bad, you can say faulty sequences is comparatively good. Overall, of course, F1 score is not that good, what we are expecting, right? So now we are just taking the classification report, and this is the classification report on the training. This is on the testing and this is on the training. Of course, we have done the training, so the report is pretty good, but that doesn't make any sense. If your model is not good on test data, whatever good it is in the training data, that doesn't make any sense. And that's clearly visible from this graph itself. For the training, it's really good accuracy, but for the testing, it's not that good. It is improving. If you take more number of epochs, maybe it will improve further, right? Or if you take more data, then it will improve further, right? So after understanding this, then we can take, this is optional, CNN and LSTM. So we'll come back on this once we finish our assessment part. So we'll definitely come back, but once we finish the assessment part, right? So again, what assessment we have to do? So what they want, look at this. So this diagram itself has all information. What we want, so previously what we have done, just you can relate it. Previously, we feeded 5 days data and we have a separate label. That label is failed or normal, or you can say failed is true or false. But what we want here, instead of predicting the fail, we want to predict day 5th outcome, day 5th data itself as an outcome, right? So what is the input for our model? These 4 sequences or 4-day sequence and 5th day sequence we want to predict. Same as if you can think of like a stock price prediction. What we do, we are taking previous 4 days of stock and predicting the 5th day stock, right? Similarly here we are taking 4 days data and try to predict 5th day's data, which contains some features that we want, right? So in order to do that exercise, what we require to create the model. So where you will create this model, so here, let me zoom, here you have this, you just click on that. Once you click, it will open this assessment. You can check out. And once you open first time, you will see here it is to do. What you have to do, here you have to only create your model, nothing else. You do not need to create training data. You do not need to train it. You do not need to create validation data. You do not need to do all those things. Just create the model structure or model architecture. How we have to create the model architecture? That is given here. So what you have to do first, you add a LSTM layer with 128 units. So it is saying 2 stack of LSTM. Means 2 LSTM layer you will create, each have 128 unit, right? Then after 2 LSTM layer, third layer will be the dense layer, it is clearly saying, and that dense layer have 256 node and activation function is 10H, right? Then fourth layer is the dropout layer that has 0.2 of the dropout, 0.2 probability of the dropout. Then next layer will be another dense layer that has 128 units, right, and 10H function. Then last layer will be another dense layer. Here you have to fix the dimension of single row data, means number of features. And where we are getting number of features? So 0, if you say train dot save 0 value, that is number of sequences, the number of data points, how many you have. Second value, how many you can say how many data points in one sequence. So 5 days are in one sequence, so that 5 come into the picture. Number of feature in each sequence, that is the third value. And how will get the third value? That is the shape of that the second 2 index, that will give this, right? So in that way you create the model. So after you create the model, what you have to do, you have to save, Control S, and after saving, what you have to do, you have to just run this cell once and run this assessment. Let's say by chance I run this assessment. Okay, just I did not done anything, so that's why it is giving error. So let me one thing. So what I have done here, let me save this, overwrite, and then I just want to free the memory and run my assessment. So because I had done previously, that's why score is 100. Otherwise, let me do some mistake. Let me do one mistake. Instead of 1, I am taking 2. Control Z, Control S. And then if I will run my assessment again, because I have done mistake, so my score is 0. So what you have to do, you have to take score is 100, means once it is say your function is correct, then you have to go to this and assess the task. Once you assess the task, you will get a message here. So take your time, next 5-10 minutes, and do this task. It's 10 minutes and do this task. In the meantime, if you have any doubt, please feel free to ask. Anyone, any doubt on this assignment? Then if you have any doubt, you can raise your hand. Okay, I think Om, you have joined just now. Okay, so let me repeat again what you have to do. Okay, so let me give you an idea. So what I have done, so here we created this LSTM model. So if you check out, we have created this LSTM model here. So I took LSTM layers from here. So you just take as it is the LSTM layers. Of course, we need two. So middle layer I deleted because that is not required. We want only stack of two. So middle layer deleted. So that is the LSTM layer. And dense layer and dropout layer I took from here. So what you have done here, you have to repeat it as per instruction. And what instructions are there? The instructions are very straightforward. Two stacked LSTM, each 128 units. Very nice. So you just copy from there two LSTM layers, put it here. Then add one dense layer with 256 node. Great. With 10H because we already have 10H. Fourth layer dropout. If you copy entire dropout automatically come. Then next 128 layer, node layer, that's also there. Last layer, it is saying it should be the dimension of single row data. And how you'll get that is the, if you say X train shape, that is the third value. So you can take it from there. And this is the way how you'll put on this and save it. And after saving, once you save it, so okay, Om is new. So how you'll get this? You have to click on this Python file and then it will open this assessment. Right? So here you will get to do because I have done it. That's why I have got here you will get to do. So that to do you have to do. And once you done, you run this cell and this cell, and here you will get score 100, means you have done your function correctly. Then after getting this, you assess the task. Without assess, do not stop. Otherwise, your assessment is not completed. So you need to assess the task. Hopefully now it's clear. I have problem in training the model block. Shreyans, now it's clear to you. Great. Yeah, Dr. Pratika, great. Please go ahead. Shreyans, any doubt? Okay, fine. Great. So after in this assessment, you do not need to train the model in the assessment. Of course, previously you have to do that to get the outcome, but assessment you do not just you need to create in the assignment, save it, and run this Python try underscore assessment. It will be done. Code you have to write by your own. I'll not show the answer code. That's not ethical. I can help you to tell, but I cannot show you the code. So what you can do, I will repeat again. You just copy these three lines and then delete the middle line, one. Then you copy all these four lines, right? Now you have to change the units as per instruction. So here units is 128, this also 128. Here it is 256, here it is 128, and here you have the shape of 2. Yes, Shreyans just explained training the model. Okay, let me do it. So once you created this model, you just take out the summary, and after getting the summary, let me close this. So what we have done here, we have just used this multi GPU. It's going in 2 GPUs because we are going to use 2 GPUs. So what we do, this is the checkpoint. Okay, let me give you idea what checkpoint means. So what we do, we consistently store the model in every epoch if it is coming better, right? So for example, in the first iteration, you save the model, then the second iteration, second model will come. If second model is better than previous in terms of loss or accuracy, whatever formula you use, let's say here monitor is validation accuracy, means if you get better at validation accuracy in the second model, so second will store, first will be gone. Then in the third iteration, if third is better, then third will store. If it is not better, then second will remain there. Then fourth, fifth, and so on, right? And it is saying patient. So early stopping. So early stopping is something if your model is increasing the validation error or reducing the validation accuracy till 20 times upcoming, it means it is there is no hope to improve further. So then you early stop, and whatever best model you have saved, that will be your final model, right? So this is the checkpointing means, right? Whatever model we have done, we compile it with the optimizer that we decided here. We are using ADAM optimizer with the learning rate, that is initial learning rate is 0.001, but we are using the decay as well. So with the number of epochs, your learning rate decay. So learning rate is start from 0.001 and slowly it will decay, right? So this is your callback list, and after that we just run this fit function to run the to start the training, right? So where we decided batch size is 16, number of epochs whatever we have given, that's 50. Validation is split is 0.1, means 0.1% will go to the validation data, and 90% will go to the training. Then verbose is 1, like every epoch you have to print something. Shuffle is true, means some data will come first, some data will come later, but here data doesn't mean one single data. It's come one sequence first, another sequence later. That's fine. Sequence means all 5 data together. It's treat as one data point here. Then callback list that we have created here, that is the checkpointing and all, right? And once we run, it will run and give you the outcome. Okay, so after saving, okay, so once you save, what you have to do, okay, let me go. Once you save it, then you have to, after the saving, you have to go to run these 2 cells, and once you run these 2 cells, here you should get 100% score. That is first. Once you get 100%, then you go back to the course and click on assess task, and then it will say yes, you have done successfully, your code is correct. Then you can stop. So check your code, what mistakes you are making, Deepak. If you done some mistakes, then it will give you a score 0. Maybe it's minor, but again, unless it's not correct, will not give you 100 score because it's like a binary 0 or 1. In order to checking, what you have to do, just if you copy paste properly and maintain the indentation and change all the things. So first thing you do, you just copy paste these layers. So first this one, second this one, make sure the indentation is correct. After copy pasting, change the units both to 128, that is first part. Then you copy this entire thing, paste it over there, change this unit to 256, change this to 128, and this, it's X train. So if you are smart enough, even that also you don't need to copy, you just need this, and done. Now more than this I can't help you out, otherwise it will be similar as I am writing your code. This you have to do some efforts, at least copy properly. So those who have done assessment successfully, please raise your hand so that I get an intuition how many of you have done. Okay, great, great. Nice. Take 5 more minutes. Good, good. Okay, so let's take, if, I think it's not good time to take a break, but let's take 5 minute break. Those who have done, they can take 5 minute break. So I will start 2:50 for the third session. By that time, others will also complete. And if you have any doubt, please post the message. Okay, that's nice. So once you successfully done, you will get similar message, score 100. Then what you have to do, you have to go to the course and assess the task. Now I will, those who have done, I strongly suggest Please see this part as well, where we are talking about the CNN, where we have 1D CNN to do the task. The only important part, data will remain same. Only important part, this model, right? So what we do, we have created 1D convolution where kernel size we have given. So this is 3, filter also 3, padding same, so that we will get the same output. Then activation function is ReLU, and input shape is data shape, and data shape we have given here xtrain dot shape 1, right? So that is the data shape. One column means 1 onward everything, so means 1 and 2, we have only 2, so we, that is the same, right? Now we have created another convolution layer where we have used the activation function. Then we add a pooling layer, max pool, where pooling size is true. Then we are using LSTM layer, right? So these will help us to find out the feature, and then we use LSTM layer to get my answer, right? So this is CNN plus LSTM. You can run this cell. Okay. Now because kernel is starting, I don't think so I will able to run it, because I have to create the data again. Do it. Yeah, kernel is ready. So okay, so it giving 1 means all previous data is gone, because I had run that CUDA, that this particular statement. So because I have run this, so it actually cleared all the memory. Because of that, I cannot run this cell without creating the data. So first we have to do all the data creation steps, then only I can run the model. But overall, we created first CNN and then use the LSTM. It's like a combined CNN plus LSTM. So CNN will help us to find out the features, and LSTM will like those features again. It's a 1D convolution, so sequence will be maintained, and based on the sequence, we apply the LSTM layer. So then you can compare, right? Okay, so that's it for this, and I'm hoping everyone able to do the assignment by now. I'm just closing this task. So once you complete the assignment, go to next, and we have very simple quiz that give the answers and move forward. So we have very simple quiz that you can give the answer and move forward. And then third assignment. So I'm running this. Okay, anyone who is not able to complete the assessment? Okay, so sir, can you please repeat once? Okay, Santanu. Okay, so let me do that. Yeah, I know it's connection failed, but I don't want to run it. I just want to explain. So you have to go directly the place where we have created the model, this model, right? You just copy these 3 lines, paste it over there, and delete the middle one. I don't think so any problem on this. Then change this unit to 128. That's the only thing we required in LSTM, nothing more. Okay, after this, you copy these all 4 lines and paste it over there. Of course, after LSTM layer, you have to paste and make sure indentation of these all lines should be same. These and these should be same. The indentation should not be wrong. They should be same. And then once you paste, if it is indentation is incorrect, what you can do, you can go to back, and once it reach in this point, your next line, then press enter, automatically indentation will be cleared. Then this unit 256, this unit 128, and here you have to do just simply this value and save. So I don't think so more than this explanation needed for this exercise. Can you just tell the error, what error you are getting? So Priyanka, you have to delete units and write the numbers. You cannot go with the units. So you have to, in place of unit, it is clearly mentioned what you have to write. So for LSTM, it's 128. For first dense layer, it's 256. For second dense layer is 128, and third dense layer, it's x train dot shape 2. Once you done this in the assignment, just save it. After saving, go back to the same place, and here you have to run this python space try underscore assessment. Here you will get score 100. Once you get the 100 score, then go to the course NVIDIA. Of course, that's not visible to me in this moment, but in this corner you will get SS task. You have to click on the SS task. That's it. Okay, so now later on you can do, it will remain with you, and once this the entire session is over, you can do it later on as well, or I will remain later after completing the session. So I'll take next half an hour at least. So wait here and help you out to complete the assessment. Okay, now it's time to move forward. So now next task, what we are going to do, we are training the autoencoder for anomaly detection. So let me launch, and I want to run this. So this I think 25. Okay. Okay, so now it's time to understand the third part, how we'll use the autoencoder for anomaly detection, right? So anomaly detection, first of all, anomaly detection is not detecting the fault. No. Anomaly is saying there is some change in behavior. Maybe it is a fault, maybe it is not a fault. But anomaly is just saying change in the behavior. It will say it is not doing the similar pattern outcome as it was doing previously when it was normal. And that is the anomaly detection. Now let's see how we'll do that. So this autoencoder is also comes under the domain of unsupervised deep learning. And this autoencoder is not for anomaly detection, it used for many applications. So I'll explain few of them, right? So this is the overall what we will do. So in this we will focus on anomaly detection, right? And we will take only small portion of hard drive for our use case, right? So this is the way how we'll do that. Let's see how we can do. So here we are looking into the third part. So let's first understand the autoencoder. Once you understand autoencoder, then n number of things will be very clear. So here you see what we are trying to do. So what we are trying to do. So first, let's understand this autoencoder part. That's really important. So what we are trying to do, just see what we have done. We have taken X as an input, right? Then you can say we apply a PCA kind of algorithm. Actually, we have not applied, but just assume. We applied principal component analysis and we take a smaller portion of that. Then again, we apply a principal component analysis. Then again, it's a smaller piece of that. And then here you have the bottleneck. This bottleneck is also known as the latent space, right? So now what we upcoming part we are doing, we are taking again, we are expanding it, then again expanding it and reach to the same level. So here if you have, for this example, if you have 100 nodes here, you will also have 100 nodes here, right? What we do, first we compress from 100 node to smaller, then again further small. It's not compulsory there should be only 3. It can be 3 also, it can be 13 also, it can be 10 also, it can be 15 also, depend upon the complexity of the problem. 3 just examples so that we can fit in this space, right? But it can have multiple. So what important, whatever input we are giving X, of course we compress it. So here let's say we have 100 cross 1. Let's say in this moment we have, let's say, half of that 50 cross 1, and here we have just 3 cross 1. So means 100 data points represented by 3 values. Now from these 3 values we reconstruct back. So here you can say this is encoder and this is decoder part. So from 3 again we try to create 50 cross 1, and again from 50 cross 1 we try to create 100 cross 1. So what is output? The output that we want to produce, that is X back. First we take smaller values and then we create X back. That is the autoencoder. Right? Here in this moment till now there is nothing like anomaly detection. It is simple autoencoder. Right? So in this autoencoder, we have taken, let's say, 100 nodes as input and 100 nodes as a output. So you can say if you make from here, it's a mirror image in this moment, right? Now you can say how we can utilize this autoencoder for the anomaly detection, right? So let's take example. Here, what we have done, we pass this encoder only with the normal data, right? and we are taking output, of course, the same data, that will be the normal data. Your model is trained, fully trained only on the normal data. There is no defective data available in this model. Only normal data has been trained. Now, if you will feed after the training, what will happen if you feed x and if it is giving x dash output, so x difference x dash will be very low. Means this error, so that's error, if you say this is the error, so you can say it is a reconstruction error. And this reconstruction error is very low, right? So now, in case whatever data you have feeded, so you have feeded normal data here, and you produces normal data here, and reconstruction error is very low because you trained the model. Now what happened if you pass a faulty data, or your model will receive a faulty data that he never seen, he never came across this kind of faulty data? Is really it will able to reconstruct the data that he's never seen? Is really it will able to reconstruct? No. And if they are not able to reconstruct, means your reconstruction error will be high. And if it is higher than threshold, then you say there is something wrong happening in my device, because your model is not able to reconstruct. Means there is a high reconstruction error, and that will treat as anomaly. So for entire training of the model, we do not need any faulty data. We are training the model only with the normal data. No faulty data here. But whenever a faulty data comes, then it will not able to reconstruct, right? Then the reconstruction error will be high. As soon as reconstruction error is beyond threshold, we'll say, oh, something is going wrong. That's why the data, what data is coming, our model is not able to reconstruct back. Means there is anomaly in my system. In this way, you are creating anomaly detection from the model, right? So there are various other applications of this autoencoder. One is denoising of the system. Suppose you want to create a denoising system. What you can do, suppose you have a good data available, good, you can say denoising song, let's say. So good songs are available, right? What you will do, you will feed here. So now you have good song, you created two different variety. One is, you say you have a song plus noise, right? You created a data where you added extra noise, external noise from the software or some way. You added extra noise, right? And then of course good song we already have. Now what you will do, you will train your model where you will feed this noisy data here. Originally you have only good song, you do not have any noisy song. So what you have done, with the help of software, you added the noise. Adding the noise is very simple. You go outside, record the noise and add into your song. Very simple. So you created the, you can say the data with the noisy song, and you feed here. So you can say this is your noisy song, video into input, and what output we look forward? Good song. Once your model is trained, after that, once you feed here any song which have noise, so then it will become a noise cancellation autoencoder. Similarly, there are many other applications of the autoencoder. So one of the application is anomaly detection by the help of reconstruction error. Getting? So what we do in our case, we will feed this sequence and output will be produced by this. So means the reconstruction, if it is very similar to the input pattern, means the error is lower. Error is lower than threshold, it means that is reconstructed well, the data is normal. If the reconstruction error is high, means there is anomaly in the system, right? So what we do here, so we have encoder unit, as I said. Here we have the decoder units. Whatever data we are feeding, it will produce some outcome, and this is the reconstruction error for simple. Now with this error, we will train the model so that this error we will be minimized. Previously in normal ANN models, what we do, we are minimizing the loss. And how you compute the loss, what output we have given and what is the original output, what is the difference between them. Now here we are saying whatever X we are giving and whatever it is producing, I want to differentiate between, I want to reduce the difference between them, right? That's the way how autoencoder works, right? So this is the reconstruction error. Why? So it will take this as an input and produce this as the output. So between difference between this and this is the reconstruction error, right? So in case of anomaly, what will happen? If it is a normal data, reconstruction is very small. But if anomaly comes, you can see the reconstruction error is very high. And that indicate there is anomaly in the system, right? So what we will do here, we will create two autoencoder. One is LSTM based autoencoder and another is 1D convolution based autoencoder. So we have already seen these two, LSTM based system and 1D convolution based system. The difference here and there, previously in the previous example, we have LSTM based system, but what we have input here, we have the sequence of data of 5 days and output is fault, yes or no. That was the output previously. Same in case of 1D convolution as well. But in this time, what we have LSTM layer. So you can say LSTM layers like this. Here you are giving the sequence of data, let's say 5 sequence of data, and output also we are producing 5 sequence of data. Same output we are trying to produce. If this value and this value are similar, you can say are similar, means reconstruction loss is low. It means no anomaly, or you can say normal. But if your reconstruction loss is high, means there is anomaly, right? So in that way we will create the model. Getting? So if it is a length of 21, so here also we will get length of 21 in the output. Whatever input we are giving, in this example, whatever input we are giving, we are getting the same output in the system, right? So how we'll do the sequence to sequence based model? We will take the input, we have LSTM stacks, we have repeat vector, or you can say latent space, then we have another LSTM space, and we have final output, right? How we'll do in the convolution 1D? We have feature 1 that will move like this, feature 2, feature 3, feature 4, feature 5, and so on. We have seen in the previous example, and in that way we will take the 1D convolution, right? So in 1D convolution, we will get output here. So you can say it will move. So 1, 2, so 1, 2, 3, 4. So here that's why for first it is one output, second it is one output, third and fourth. And we have those many features, they are similar as here. So 5 features here, 5 are here because it's movement 1 currently, then 2, then 3, then 4. So we have 4 outcomes here. So in that way, your 1D convolution will work. Getting? Right? So for more detail, you can take this paper itself, but more how the architecture will be look like. You have 1D convolution, then max pooling, then again smaller 1D convolution, again max pooling, then again another 1D convolution, then upsampling. Important part. You check out here, important part, we have 1D here and we have upsampling here. So you can say if you take this out, this and this are similar in nature. Upsampling 1D, upsampling 1D. So if you have 5 cross 21 as input here, so output also you will get 5 cross 21. Similar, right? So this way you will do the 1D convolution. Now here we have one more curve, that is the ROC curve. That is very important. What ROC curve is doing, they are comparing the robustness of the system, right? Robustness means how, because here we are saying if it is more than threshold. Every time we are saying if reconstruction loss is more than threshold, then we say anomaly. So when you say threshold, so what should be the good threshold? Or really our system is able to understand the threshold well or not? So what we do, we are doing creating the ROC curve. What ROC curve is doing, so it is the plot with respect to false positive ratio, false positive rate and true positive rate, right? So this line is really important, right? So threshold is high at y-intercept, resulting 0 false positive, right? While low true positive rate. As threshold will decrease, true positive rate will increase, so false positive will be, but the false positive rate we want to maintain, right? So that should not be increase, right? So in that way we have to maintain the threshold, and once we plot we will get this outcome. So here you can say if you have more closer to this, that is the best case, and this area will say that is the EUC, area under curve. If you have maximized the area, then it's better, right? So this is mainly handling the threshold, effect of threshold, right? That will come into the picture. So some example, if you say you have this probability is 0.5, you have very clear picture, 0 to 0.5 is this, 0.5 to 1 is this, means there is no overlap, then AUC is very high. But if you say there is, of course, overlap is there, right, then AUC is very low. So this ROC curve help us to understand how good our model, how robust is our model, and is really they are able to separate our good data and bad data very well. So if they are able to separate very clearly, here it's very clear, they are able to separate it. So means your AUC is very high. And if they are too confused, they are not able to separate good data and bad data at all, then AUC is very low. Right? So that's the way how ROC curve help us to find out the outcome. Right? So how we'll do this sequence to sequence model? So first we'll create LSTM. So here we have the input layer 16 cross 21, important point, 16 cross 21, and once we take output, that also should be 16 cross 21. First we increase, then decrease, right? That's the way how your autoencoder works. Input and final output should be same, right? So how we'll do that? You will simply take this. So you will say encoder, and here we have LSTM layer, similar as the previous, the LSTM layer. Then again you have a decoder, right? So in this decoder we have encoded, added this layer, and here we have this data. That is the, then again we have the decoder. Here again we have another decoder, and finally we combine these input and decoder to make the entire model. Right too. So important part, previously what we have done in the lab 2, our model have LSTM, then dense layer, and the outcome. That is one, it is fault or not. Here we are not saying fault. What we are saying, if you check out this data shape 1, and whenever you take the input, that is also the same data set, right? So in that way, so we will take the model. So you can say we are creating the model. So first input shape is the data shape that we have, and output should be the same. It should not be differing, right? So input and output will be same. So in the lab 3 we will create LSTM like this for the autoencoder, but in lab 2 we created like this, right? So it's a summary of that how we'll create. So here we will feed all normal data, for the training, simply, and we create a AE model. Now, in the inference, we create any one set of data to the AE model and we reconstruct the sequence. And if this sequence is similar as what we have fed it, means reconstruction loss is very small, right? Then you can say my device doesn't have any anomaly. But if your reconstruction loss is high, in that case, you can say my device has some anomaly in the system, right? So now let's move forward. Go back to the lab. Going back to the lab. Hopefully it's started. So let me launch it. So I want to give you. Okay, let me quickly explain it. Then you can do it. What we want to do first, one question. You can answer in the chat box. For this anomaly detection, do we need faulty data for the training? Just put on the chat box. Yes, no. Correct. We do not need faulty data for the training. For the testing of this model, do we need faulty data? Yes. For the testing of the model, we need faulty data. Why we need faulty data? Otherwise, how we'll check whether our model is able to detect the anomaly or not until unless we'll not feed any anomaly data, right? So for checking, only for checking, we need some faulty data, but for training, we do not need any faulty data. So you can think of, suppose you started a new company, you have installed a very big machine, and suppose someone will say, okay, I will do the anomaly detection, give me some data. So of course at that time what you can do, because there is no fault, so you do not have any faulty data, so lab 1 lab 2 will not be useful. Why it will not be useful? Until unless you do not have fault data, how you will train your model? Then lab 3 will be useful because you have good data available. You train your autoencoder on good data, and whenever your autoencoder will create more reconstruction loss, that will indicate there is some anomaly in the system. Please check your system. So even if you have created very new plant where we do not have any fault, then also with the help of anomaly detection, or with the help of autoencoder, you can use the anomaly, and that's really useful, because most of the cases someone will say, okay, I want to use the machine learning or deep learning to identify the fault. When we say, okay, can you give the data of fault, then say fault happened only once or twice in a year, so I do not have data. Then you say, I cannot create a fault detection model. But instead of that, what you can say, okay, there is no faulty data, that's fine. What we can do, we can create an anomaly detector for you. That will indicate you there is something wrong happening in the system. In that case, you will utilize this anomaly detector. Okay, so let's move forward. So here we have the similar explanation. We have the input. Let me zoom a little bit. We have the input. We have given this input and try to reconstruct back. Okay, few interesting application, because let me take 2-3 minutes to give you few more interesting application, which is with this autoencoder. Just think on application of black and white to color image. Color to black and white is very simple. You just convert into the grayscale, you will get. But black and white to color is difficult job. There is no straightforward function that you can apply, and from black and white you can get the color image. Very difficult. What you can do, you can use this autoencoder for the same task. Now you can say how we can train the autoencoder. Simply, you have n number of colored image. You take those color image, right? Convert into the black and white, and those black and white image will be input of your autoencoder, and color image will be the output of your autoencoder. At that time, okay, so let me open the chat box. At that time, do you feel your input and output will be same, or there will be different? Yes, exactly. Whenever you say the output, there are multiple channels. So if your input have 10 cross 10 cross 1 in the input, so the output will have, because it's color image, it's a 10 cross 10 cross 3. In that case, the output, if you say the output here, that will be 3 times higher than the input. Then only you can convert black and white to color. Getting? So in that way, you can use, you have another application. Similarly, many more applications for this autoencoder. Okay, so now let's move forward. So here we have the autoencoder. I hope it's very clear. So we have this reconstruction error. What we want to do, whatever x we are feeding, in this example, whatever x we are feeding, we are trying to get the same x. Whatever difference is coming, that is your reconstruction error. So let's run this cell to get all the libraries which is required. So it's a min-max scalar, scalar in the pre-processing part, right? These all very standard libraries, so I'm not jumping into that. Then we do the train test split to check what exactly going on. Then we will use ROC curve, AUC, precision recall score, F1 score, all those to understand the performance of the model. Then we will use some sequential, then we will use the optimizer ADAM and RMS prop. We will use model checkpoint, and of course we are going to use LSTM layer, leaky ReLU, dense, flatten, dropout, and all those layers to do the task. So let's run this cell so that we were able to load the library. Now, of course, after loading the library, we need data. So let's run this cell to load the data. Now, reading training and validation data. Fine. So, of course, with the same model, we are reading the data. So we have total data is 74,000 cross 46. Right. If you want to see the data, you can check out here. So these all data available with us. Right. Now what you have to do, we have to remove the normalized that we have done previously. We just remove the normalize. Now we have to find out the labels. Where is the label? In this data, I will find out the label. Yes, anyone? Okay, let me check. Message on chat. Yes, label is input itself, right? So what we will do, let me go to, so retrieve the output label. So let me see, what is that? These are the failure values. Why these are the labels? Only failure. We are not worry about the normal. Only the failure values, because that's we will check later on. Not for the training. It is not for the training. It is only for whenever we test. We will not utilize for the training, right? So let's take this so that we will get the labels. Now we want to sort the data for autoencoder based on the sequential ID, right? So we are just sorting the data based on the sequential ID. And after sorting, we are resetting the index so that we will get the same index. So here we will have the ID. These are the two IDs. So based on that, we sorted it. So you can see AE sequential data ID is given here. So based on that, we sorted. So this is nothing. It's like a disk one, model number 1, 2, something like that. So accordingly, we have sorted. So we are taking only small data. 32 rows and 46 columns. Not too big, so that it will take lesser time to do that job. Right? Now we want to remove the columns, data, serial number, model, failure, capacity bytes, that we already done previously. So you are well aware why we want to remove this. Now we want to clean. So we just clean the data. So remove the normalized column because we already have the raw data. So we remove the normalized column, right? And after removing the normalized column, the raw data we normalized by our own. We normalize by our own. So here for LSTM we are using this. So how we normalize? After normalizing, we are reshaping X shape. So how we saved it? You can check out. We saved it. Whatever total data, divide by sequence length. Whatever sequence length we want to give. Suppose we are giving 5 length, so 5 data will come at one go, right? So that will give how many number of data points, sequence length, and shape, how many features we have, right? Accordingly, we will use this size. So let's run this. Okay, so just we are running this particular pre-processing, so we are cleaning the data frame and we are normalizing what we have initialized previously. So after that, you get this information. So this much data we have available with us. Check, you will get this outcome. The total, what sequence we have taken, it's a 16. So it is given somewhere, the sequence length. Yes. What sequence length we have taken? 16. Using 16 days sequence. So that's why your window size will be 16. Previously, in previous example, we was taking only 5 days window. So that's why sequence length was 5. We are just for so that we will able to do quickly. You can go with the 5 length as well, but here we have taken sequence because we want to do it faster. If you have more sequence, means lesser number of data points. Okay, so now same thing we are doing for the test data as well. So total number of test data is 834. So now here 834 is number of sequences that will be created. It's a data points. Every data points contains sequence of 16 and have 21 features, right? So in that way, your sequence has been created. So you can check it out like this. Now here filtering the labels. So as the class label, there is no extra filtering step. So just take some time to find this out, why we are doing this, why we are filtering the labels, because we do not need those labels, right? So that's why we just filter it. Okay, now let's run the LSTM. As I said previously, LSTM was the LSTM layer 1, 2, 3, then dense layer. Now here we have only LSTM layer. So we have input shape, right? So that the data shape that we have given. Then we have created LSTM layer as previously, right? Then we have repeat vector, the encoder part. Then we have another LSTM layer and last LSTM layer that will produce the output. And once you run it, you will see something very important. Check out here. Input shape 16 cross 21. Getting? And output, what we are getting? Again 16 cross 21. Whatever input we are giving, 16 cross 21, same output we are getting. Now in between, you can increase and decrease. In this part, maybe you don't like 2 layers of LSTM. Maybe you want to go with multiple layers of LSTM. So instead of saying like here we have 16 cross 21, they at 128, then this is 128 vector, then again 128 and getting it back. So instead of that, you can say I want 128, then 64, then 64, then again 128, and then I will give this vector. That's also fine, right? So in that way, we created this LSTM based model. Now again, here we have the checkpointing. So we use the model checkpointing to get the like store the best model with the help of checkpointing. And after that, we are training the model, this autoencoder, for 60 epochs. So by that time it is training. If you have any questions, please feel free to ask. Just anyone, any question if you have, please feel free to ask. Okay. So the beauty here, it stops at 28th iteration itself. But we have given 60 iteration and it stopped because of early stopping. So what happened previously? Why it stopped at so early? So here we have given 20 patients. Means after 8th epoch, so if you say first, second, third, fourth, fifth, sixth, seventh, 8th epoch, you are getting model that is the validation loss is 0.2082. That is the validation loss. You can check out. Then further, next 20 iteration, your validation loss, if you check out, is increasing. It's not decreasing. So it wait till 20th iteration and then you see no, there is no hope of improvement, stop. That's the early stopping. Right? And this is the best. So ultimately what we'll get, we will get the model which was created in 8th epoch, that is the best model, and that we will get. So that's why you can see as soon as we move forward, it's improving, model has been created. But after that, no model created because we are not getting better. So that's why no model is stored. Getting? So previously it is saving the model because we are getting better model. So that's the way how we can implement the early stopping. Now let's load the weight of best model that we have stored and see the outcome. So this is the way how your model works. So it goes loss. So this is like in 8th epoch, we got the best model here. Then it is increasing and going forward. Maybe if we go little more longer, we'll get better. But because we have the early stopping, it stops here itself. Right? Then let's see the prediction. So let's print this particular prediction. So you can see the blue is your normal data and red is the predicted data. And what this record are saying, that is saying this is anomaly. Why this is anomaly? Because if you check, this is very far, this is far, this is far. They are not overlapping. Means they are crossing the threshold. That's why we are saying this is the anomaly disk. The disk is because the reconstruction error will be very high between red and blue. That's why we will say there is an anomaly in the system. Right? So let's measure the error. So suggested threshold is 0.17. That is the threshold. Like if your error is more than this, then you can say the reconstruction error is more than this, then this is the anomaly in the system. Right? Now let's look into the 1D convolution method. For 1D convolution, of course, we need to create the data point. So we created the data checkpoints here. And now we are creating the 1D convolution. So this line is not important for me at this moment because the 1D convolution we are creating here. Right? So dropout rate 0.2, outside filter is 160, inside filter is 80. So what it will try to do inside outside filter means, okay, let me take some space somewhere. Do we have, okay, let me take this itself. So what outside inside means, So it will say this is your outside filter, this is your inside filter, this is inside, this is outside. Means outside filter we will take 160 and inside filter we will take 80. So in this way it will create it. So let's see. So here we say first convolution outside filter means 180 filters will be created. Then we have max pool layer, dropout layer, then again convolution, this is inside filter, 80 filters will be created, then again max pool, dropout. This is the encoder part. Here we have final encoding, that convolution 1D with filter 4, only 4 values in the center, right? Then we do the upsampling. Like previous we are doing the max pooling. So max pooling, what max pooling is doing? It is reducing the number of values, right? It is pooling, it is doing the max pooling. Now here we do the reverse of that, is upsampling. Sometimes in many places it is also known as the unpooling. We will do the upsampling with the 1D convolution with 2, and then we take 1D convolution inside filter, then again dropout, then we take upsampling, then again we take 1D convolution. So it will create a structure as we have seen in this diagram. So first this is an encoder and then decoder. Okay. Now let's run this to see. You can see one important point. Here also it's 16 cross 21, that is the input. So what output we look forward? Same output, 16 cross 121. So you can see here 160, 160, 160, then 80, then 444, then again 80, 80, 80 and 160. So means whatever size we are taking as an input, same size we are taking as an output. Now the beauty here, this concept further expand and heavily used on the segmentation of the part. If you say image segmentation, so similar kind of autoencoder structure used for the segmentation as well. So while you do the segmentation, they also use the similar autoencoder kind of structure, like the IC UNet or VNet or ResUnit. They are using similar kind of structure. Okay, so now let's run for 100 epochs. And you see like it's very fast compared to the LSTM. It's done with the 100 epoch. Let's save the best model and see the graph. So this is the way how it works. So here we have the training data. This is the test data. So it is data loss, validation, training data loss, and that's reducing. And let's predict from the test and see how it looks like. So now this is your blue and this is your red. So somewhere it's go up, somewhere it's go down, right? And they are saying the difference is not too high. Previously the difference was, many places difference was too high. Here only few places difference was there, like here rest are very closer. So you can say your overall reconstruction error is not too high. That's why it is saying this is a normal disk, right? Now let's run this cell. They are also suggesting the same threshold, that is 0.17. Okay, run same record. So it will, we will find out on our data, the current data, they are saying 601 are the normal disk once we pass the entire data, and then you will say 233 is the anomaly disk available based on the given threshold and which is on the test data, right? Okay, now let's see how ROC curve is working. ROC curve, as I explained, they will give you like, they will, what we will do, we will take the threshold from, let's say 0 to 100 or 100 to 0, one direction, and as soon as we change the threshold, we will check the true positive and false positive, and that will become true positive rate and false positive rate. We will plot them and that plot will give the ROC curve. So let's run this. So this is the ROC curve for LSTM, and let's run the ROC curve for this. So this is very closer. It's very difficult to say either this is good or this is good. But if you check the numbers, then you can get an idea. So can you tell which one is better, first or second? First is better or second is better? Here area under curve is 0.71, here area under curve 0.73. So if you have higher area under curve, that is better. If you have lower area under curve, that is not better. So with this, you can easily figure out, so this is much better than this, right? So now we just take the classification report of this like this. So they have given this classification report, and it's clearly visible. This LSTM based AE is giving better results than your 1D convolution based AE. But compared to the training time, or you can say compared to the execution time, you can see a 1D convolution is also doing a good job. I'll not say better than LSTM, but doing a good job compared to how much time it is taking for training and all those, right? Okay, so now this is the like a stopping point here. We have few more experiment related to hyperparameter optimization. So before jumping into the hyperparameter optimization, or let me take 10 minutes to explain the hyperparameter optimization, and then we will move forward. So in this exercise, we will use Bayesian optimization for hyperparameter optimization. Now first question comes, what is hyperparameter optimization? So here few parameters that you decide to create the model. For example, how many units in LSTM layer? That was one parameter that you decided. Similarly, what should be the learning rate? That also you decided, right? Similarly, number of nodes, or what will be the kernel size? That also you decided, right? So these all are the hyperparameter. What should be the best hyperparameter so that we will get a good model, right? So in order to study that, we are using hyperparameter optimization. So hyperparameter optimization is something where we will try to systematically find best those parameters. Now you can say there are two things. One is the weights of the model, that is trained by the training data, that will find by the training. Whenever you feed, it will find the weights of the model. But the architecture of the model will be found by the hyperparameter optimization. Once architecture fixed, then it will not change during the training. Getting? Only thing what we can change during the training is the learning rate, that you can change. But if you say number of layers, number of nodes, what will be the activation functions, these all you cannot change during the training time. So you have this method will help you to find out best learning rate. This method will find out best hyperparameters, and that is impacting the entire system, right? So just one example, if you are aware, there is a efficient net, and this hyperparameter optimization expansion is also known as model architecture search. During the training, you will find out which architecture is best for you, and that is, you can say, extension of hyperparameter optimization, and it's a really good field in this area, right? So now let's see how Bayesian optimization works. So here we have like these are some graphs, so I'm not jumping into that. Okay, let me give you some idea behind the Bayesian optimization as well, broadly how it works, not very deeper, but broadly. So Bayesian optimization started a long time back, that is the probabilistic based model. And this Bayesian optimization is very useful whenever testing a particular sample is time consuming or very costly. Costly in terms of time, maybe costly in terms of power, maybe costly in terms of other things, right? So that is difficult, right? So what we do in the Bayesian optimization, first it will fix one point, any point randomly. Then based on that one point, it will find out what are the probable good points next that you need to explore. So this Bayesian optimization is started to find out where you have to make the hole to get the fuel out. In long time back, whenever you means whenever fuel wells we are searching, at which place you will do the hole so that you will get the fuel. In order to solve this problem, Bayesian optimization comes, because you cannot randomly put multiple holes across the earth, because creating a hole is very costly. So that's why they make the hole, find out the different parameters, and based on the parameter they will use the Bayesian optimization to find out where they have to put the next hole. In the same way we are doing in our experiments as well, right? So what we do, we simply say we will take the you can say parameter, and then we will compute the function that is the that will give you is really it is optimized or not, right? So here you have a way to do that. First we create a function. What this function will do, the function will have hyperparameters. Let's say we have the function of learning rate, that is one parameter of the function. Let's say number of LSTM nodes, that is another function, the parameter of the function. Now this function will do one job. It will, so it will do, once we'll pass these two values, it will create the model, train the model, and return the, let's say, validation loss as a return. That's one function is doing. This will become your objective function, and I want to minimize the loss, or let's say it is returning the accuracy, so I want to maximize the accuracy. So this function I want to optimize with the Bayesian optimization, right? So let's take this. Actually this you can do later on as well, but I want like just give you a walkthrough. So here we have the hyperparameter like min max, and we have the count, right? Then is really it is a scalable linear or float type or type. So these are different variety of parameters that you can take, right? So we can set minimum value, we can set the maximum value. So these are some self set parameters. These are known as a setter and getter. So these are the setter and getter methods for this. So it's like update method, unscaled, from scaled and unscaled. So these all methods we use to run the this Bayesian optimization. Then here we will use to just plot the history. So this is just for the plotting, right? Now this function is really important. What it do, it will take the data set, it will take the parameter list and create the LSTM model. Here it create the LSTM model and return it, right? So it will create the entire LSTM model. So you can say, so now you can say from where you will get. So you will say first model parameter is LSTM width. How many, what will be, like previously we say it's 160 or 80. That is coming from Bayesian optimization. What should be the width? What should be the learning rate? So these two things we are taking from the Bayesian optimization. What should be the learning rate and what should be the LSTM width? And you can see here we are using that value. So whatever coming from the Bayesian optimization, it will pass through LSTM and it will create the model. After creating the model, it will return that model, right? So let's run this cell. Then this is just to printing different history, so only for the printing. Now finding the loss. So what it will do is plot the model loss. So every iteration, what will be the loss value? So we are printing only that part. Similarly, we are plotting the loss map. how the loss has been changed. So that we are printing here. Now let's come to the main method. So here we have defined one method, that is train and fit. What train and fit is doing? So this method, here we pass two parameters, as we say. One parameter is the width of the LSTM layer, and second parameter is the learning rate. Now based on these two parameters, we have created this function that is returning the model, creating the model and returning the model. So we are passing these two parameters here, and it will create the model. This line will create the model. After creating the model, we create the checkpoints as we have done previously. We create the checkpoints, we use early stopping, we use the optimizer, and then we fit the model, right? And after fitting the model, we will send the result back. Result means whatever loss is coming, that we are sending back, because this result will help us to find out the new parameter, right? So now let's see how it works. So we have hyperparameter, we have created the range. So minimum number of nodes 32, and maximum number of nodes, it can be 128. So now here you have flexibility to decide what range you want to iterate through. Count, we can fix the count. So what is the maximum? So we fix as a 15. Type, it's integer type, right? Similarly for the learning rate, what is the range? Minimum is 0.0005, maximum is 0.1. How many such data will be created? 15 such data will be created in this range. And what is the scale? It's a logarithmic scale data. So now we will create this entire data. After creating the data, what we'll do, we will run for train and fit. So we'll see, we will just start with this first train and fit. So if we are here, we are not running the optimizer in this one, just we are checking by sending one data. Like here number of you can say simply you can say width of LSTM is 80 and learning rate is this. So how this train and fit model will behave, just we want to check that, right? So if you run it, you'll, okay, something is wrong. Okay, this I didn't run, sorry. Now let me run this. So it will first create and train for 20 epochs, this one single function, where these two are the variables, and these variables will be decided by your optimizer, right? These will be decided by optimizer, right? So what we will do, let's see in the optimizer. Now here we have the main call, right? So here we have given what Bayesian optimizer we are using, what function we are going to optimize, this function. This is what I want to optimize. What this function is, it will first create the model, train the model, and return this value, right? So that is the value that we want to optimize, right? That is the objective value that we want to optimize. It is given here. So this is the function that we want to optimize. And here, of course, bound, what is the min max range and the state. So we can start with the random state. So now this will take too long. So before I'm stopping here before running this. So what it will do, it will go, so you can say iteration 1, it will get this width, this learning rate, and run the entire thing and get the optimization value. Then second iteration, it will get this and this value, then run the entire thing and give you this optimization value. So I'm not running this because it will take like very long time. So not running in this moment, but you will get this outcome. So what this outcome is saying, first iteration, it has STM width is this, learning rate is this, and then you will get the loss function, loss of this. Then you have second 22 this, and then loss of this, and so on. So in that way you create the entire sequence, right? And after that, so you can say, because we created the maximizer optimization function, So whenever it is the maximum, so you can say when it is the maximum, at that time you will get the best values, right? In that way you will get the final outcome. Okay, so that's it for today. So once we'll run, you will get all those, like in every park what we are getting. So this is the best curve that you will get, and similarly this is the worst whenever you have different. So you can say width is 68, learning rate is this, so optimized objective value is this is the worst curve, right? And this is the best curve whenever your width is 116 and learning rate is 0.035, that is the best curve. So the beauty here we are using only two parameters. Similarly you can use n number of parameters and decide which one is the best model. Only challenge, the time will be very high. Comparatively with other methods, it is very less, right? So that's it. Then here they are saying like you can do some to-do task here. So this part. So train and fit if you are using the particular 1D convolution. So how we'll make this? So just you can do it by your own, and then you can complete the lab. So from here onward, it's like some self task that you will do the repetition as similar as previous, where you have a different model to do. Right? So instead of this train and test, we have again LSTM encoder to have two parameters, and that we have to optimize. Okay, so that's it from my side. Now after completing this, what you have to do, you have to take this third quiz, and this quiz is very crucial because it's contain 40% of the marks. So make sure you do not make any mistake, right? So here we have like which statement is not true for autoencoder. Then here we have what is ROC curve, so you can easily find out like threshold setting. Similarly, which statement tan H or sigmoid activation not accurate for this. So of course sigmoid range is not -1 to 1, right? Similarly, you can say which category problem is not applicable for autoencoder. So time series prediction you can't do with the autoencoder, right? So in that way you can do the quiz. So that's it from my side. So now once you complete, please make sure you fill the feedback. Now I'm stop the sharing and open for the question answer if you have any. Where are waiting? Yeah, if you have any questions, please feel free to ask. So now you can go for the, after completing this to do, there are only two to do in this lab, third lab. Then you can jump to the quiz. Make sure you are doing the quiz very well. And after that, you can generate your certificate. So I'm here for next 10-20 minutes. If you feel any difficulty, please feel free. So if you have any difficulty, please send me on the chat so that I can help you out. So what you can do, you can simply go to the task 1 and run it and complete the, there is a self-explanatory things that you can do. So just run it and see the results. So you just run the, if you feel any doubt, please report it here so that I'll explain. So any problem in the assignment quiz, of course, you have to do by your own. Okay, once you complete all 3 quizzes, what you can do, let me give you idea what you can do. If you complete all 3 quiz and the assessment, then you can generate your certificate. So how to do that? Let me share. Okay, once you do all this, you can go to this progress. Here we have the progress bar. And once it complete, it will cross your 90%, then you can request for the certificate. So once you request, you will get your certificate. Because one task I have not done this to do, that's why it is showing 88%. Let me do that. So of course, this is the graded point. So here, you will get all the scores, and that score should be in total more than 90%. So let me do that to do. These results we cannot produce because I have not run the Bayesian optimization. Okay. Okay. Now, if you run this, it will take some time to complete. But anyways, if you have done everything, then if you are passed, then you can request for the certificate. How to complete? Okay, second assessment. If you have not done yet, what you can do, you can go to the course. Of course, open the second task again and directly do the assessment. Don't run entire thing, directly do the assessment. So you just need to run this second task again. So once you run, you will get the assessment part and complete the assessment. Once you start, you will get similarly as lab 2, and you go to the bottom, open the assessment part, write the code on the assignment, save it, and directly run it. You will pass it. You do not need to redo the entire thing again. Directly you can go for the assessment. Okay, any other question? Any other doubt? Anything where you stuck? Please try to complete here itself. Okay, can you raise your hand like how many of you? Yeah, yes, Jeet. Jeet, Shreyans, you raised your hand. Any question, any doubt? Okay, those who have completed, please raise your hand. Those who have completed all assignments. Okay, nice. Yeah, yeah. Take your time, not a problem. So that particular Bayesian exercise will take time. It will take time. Because what you are doing, you are creating a new structure every time and train it. Then new structure, train it. And you do this 16 times. Because you have created 16 subspaces. You do it for 16 times. That's why it is time taking. Okay, L1 and L2 regularization. Fine, fine. So this first of all we need to understand simple regularization. So regularization, okay, let me take some space to explain the regularization. Okay, so in general, regularization is something when you say you are forcing the system to reduce or make a definite range. Let's say, let me take example. Suppose we have a loss function. So normally what loss function, suppose we are taking a regression problem, then we have a squared loss. Suppose we are taking a classification problem, we have log loss. Let's take example of regression problem, and we have required loss y cap minus y whole square, right? That is the squared loss. So take 1 by n so that we can normalize it. And if you write in a better way, so let me do in more better way. So you can say summation 1 upon n, we have I equal to 1 to n, and then y cap of I minus yi whole square. That is the squared loss, right? Now what we do, of course, if you say the neural network, then we have the weights. So we have lots of weights available. These are the weights that we want. Let's say here we have the output, right? So in the neural network, here we have the weights, W, here also W, here also W. Okay, here we do not have W. Let's say these two layers are there. We have some Ws. Now, what is the role of your gradient descent? That will say find values of W such that your loss should be minimum, right? In order to do that job, what it do? It will increase few weights by high, so that it will understand the system, and by understanding it, it will increase the value of W's, so that your loss will reduce. Either it will increase positive side or negative side, but it will increase the value, right? And this is the way how it will reduce the loss. But what happened, once you increase these W values very high or high, listen, comparatively high, then when new data will come, or you can say test data will come, then your performance is low, because you have trained model too much for the training data. So for training, it has very less loss for the training, and high loss for the testing. Why? Because of weight values are very high, to reduce the loss of the training, right? So now what we do, let's take example here. So let me rewrite loss function 1 by n summation I equal to 1 to n y cap minus y square, right? So now what you do, you add one more term, and that term is this value. So if you say this, that is the L2 norm. And another choice, you can add this as well. This is the L1 norm. So how it is different? So you can say this L1 norm is nothing. Suppose it's a something. Suppose you have weights, m weights. So I equal to 1 to m. I equal to 1 to m. And here you have Wi. And here you are taking 1 upon m. This is your L1 norm. You normalize it. Just you are taking the average in short. Now here you will take the mod value. That is important. Means either it's negative I or positive I. Both will consider as positive, and you will take the value. Now in the L2 norm, what you will do? You will take square root summation I equal to 1 to m, and you will take W of I square, and here you will take 1 by m. This is L2 norm. You are taking square of the values, and then you are taking the normalization, right? That is the L2 norm. Similarly, you have L3 norm, L4 norm, L5 norm, and so on. That is the way how L1, L2 norms comes into the picture, right? So that's the L1 and L2 norm. And what it do, now let's understand why it is important, why it is a regularization. So the regularization, now you can say new loss function will be this. So let me take another. So new loss function, you can say your loss function will be it will be a y minus y cap. Okay, y cap minus y square equal to 1 to n plus L2 norm of W. So now you can see this part will increase the weight, and if this increase, this will also increase. But total loss we have to decrease. In order to decrease this, so suppose your weight is decreasing high, then this will be increasing. And if this will increase, then weight will also increase. So then the challenge, so this if this will decrease, weight will increase, right? So it's help us so it help us to find out the best value of W, not very high, not very low, the best value of W, so that your validation loss will be reduced or validation accuracy will be reduced. And that part is known as the overfitting. So it reduces the overfitting, right? That's the purpose of this L1, L2 norm in this place. No, it is not helping exploiting and vanishing gradient. This is helping to reduce the overfitting problem, because they are associated with either weight, means in the loss, or they are associated with activations as well. You are doing a L1 norm of L2 norm of activations as well. So that will help us to maintain the sparsity in the system, and that sparsity help us to reduce overfitting. It is not helping in vanishing gradient or exploiting gradient. For exploiting gradient, you are using simply clipping method, and vanishing gradient, one method that I explained, like instead of if you are using CNN or something, you are using ReLU. ReLU evolves just because of vanishing gradient. Then there is a like a resonate, where you have a recurrent value, so the input will go and jump to the another output. So that also help us to the reducing the vanishing gradient. So resonate unit, you can see the resonate units, like we have LSTM. There is one unit which does not have any activations. Similarly, in the resonate also, they just pass one unit to next iteration, or you can say next outcome, directly concatenate. That will help us to vanishing gradient. Yeah, I hope most of you have done. Any questions if you have? Else we are closing the session. So tomorrow you will see the transformer in the next third session. It's very interesting. Okay, so now I'm stopping this task. Yes, Pirangi, Jeet, any doubt if you have, please send me over the chat. After completing all the tasks, getting only 63%. You can check in your progress where you have made the mistake. So how you can do that? You can go here and see the progress, and this will give you an idea how much you got. So here it should be 100, 100, or similar values. So if you made a mistake on quiz 1 or quiz 2, again I say if you do it more than 2 times and then you got the answer, that will consider as incorrect. Or if you have not completed this coding assignment, then it will be lesser. So let me share. So from here you can see where the deduction happened, and even you can see here as well the scores. If it is a task 2 assignment, then it's not a problem, you can re-achieve. So have you completed like more than 90% Shiv Shakti? Then only certificate. Okay, so then it will generate the certificate. Just refresh it or re-log in, it will generate. Okay, task 2 assignment and Dr. Ingrog. Okay, let me give you an idea. So here we have to add the LSTM layer with 128 unit. So this is like one layer. This is just one layer because the space it is not coming. Then add another LSTM layer, then dense layer, then dropout, then dense layer, and here it's a train shape 2. That's it. Just you have to copy paste from previous. Don't type, only type the values 128, 128, 256, 128. Do not type anything. Another thing, ensure the indentation. That's it. Yes, Jeet, Mohammad Asfaq, any question if you have? So just re-log in. I hope this will be gone. So thank you everyone, and I'm available for a few more minutes here if you have any problem on the assignment. So those who have done, they can leave, enjoy.